Hello, everyone. I'm Chuck Chapman. I'm going to be presenting today on powering in the HFC plant. There's a lot of different items I wanted to cover. There were some scheduling changes, so I'm going to have to try to get through this very quickly, and we'll get through as much as we can. This is a very interactive. Presentation. You're going to see me kind of going back and forth to do things on my computer. There is a link to Mentimeter, which is an online scope. So here's something you won't hear very many presenters say. I want you to have your cell phone open during my presentation. And what I'm going to do is in a few minutes I'm going to bring up a link, and all you have to do is press on that link, and it'll bring up a window, and it'll ask you a bunch of questions. And then what you do is you answer those questions, and we actually work interactively. So it's kind of a way for me to learn about you guys, so that when I present, I'm presenting to your level. So you may see me very rapidly go through a bunch of slides because it's like, okay, you guys already know this. So let's go ahead and get started. First of all, the SCTE has all sorts of technical tools that are available. Tech Tips Primer Series, live learning webinars, and the SCTE Infoscope. There is a great deal of SCTE certifications. The one thing I left out in the questionnaire is, what certs do you currently have? George Bozak, who actually worked on a lot of the presentation material I'll be delivering, has pretty much all of those. It's crazy. He's a great technical resource that we use. There's also the career tools, the SCTE Foundation grants and scholarships. You can just click on this link to go to the SCTE site to follow up on that. And again, lots of networking tools. These will help you in your career. And the Cable Tech Expo is always great to go to. Actually, last few years I haven't been able to go because they haven't had it. This year they did have it. But make sure you schedule next year, October 16th and 19th in Denver. Okay, so here we go. This is what I was talking about. This is a QR code. Just take your camera, point it toward it, or you can go to this site and actually click, and that will show you the questions. So now, how long have you worked in the cable industry? Here we go. And the cool part is you guys get immediate feedback. So far, and that goes for the people in this room as well, right? Do you want me to bring that QR code up again?
I did. No, we got it.
Okay.
Hey, could you go back? Sorry,
Yeah, I'm going to go ahead and go back and just maybe I didn't stand that long enough. There you go. And you know what I'm going to do? I'm going to go ahead and log in and do this myself. So I take my cell phone, I go to my home screen, click on my camera, click on the link there. And let's see, I'm in the over 25 years category. So just to show you what it looks like on your screen, can you give me 1 second here? I think I can do it this way. Give me 1 second. Here's my laptop. Should be there. So this is what you should be seeing on your screen right now. Oops, click on the right link there. Is something like this. Okay. So sorry, my scroll it down. And all you have to do, you just click on the one that applies to you. Click submit. So I know that's a little bit of an extra step that not a lot of people need to take, but just something that we'll be using throughout the presentation. So this is giving me a better idea. So currently within the attendees, we're ending up with a lot of people that have over 25 years experience in cable. So it's interesting, 10 to 15 must have been something interesting. I'm going to have to look historically to see what happened in that, where during that time frame a lot of people didn't actually jump into cable. But you'll notice that there's a vast amount of people. Cable is a very good industry, to be honest. It's taken care of me for over 30 years. And that's one of the reasons I like to get back. The SCTE is open to having other presentations as well if anyone wants to jump in and contribute to the industry as well. So we do have a lot of very very mature, well-trained people in the industry. So let me ask you the next question. What training items would you like to have covered this year? Now this is a little bit of a different one. What you'll see, again, on your Mentimeter screen is something like this. Enter a word.
Yeah.
So let's just say, by the way, I'm also the chair of the SCTE DSS Committee on Smart Cities. Let's just say that I'd like to have training on powering. And then training on, of course I have to spell powering, right? And then training on, let's see, HFC. Click submit. So as you guys go ahead and load in the things that you'd like to see training on in the upcoming months, just go ahead and click it in and we'll take a look at that. Of course I spelled cities wrong and I'll pay for that forever. Do you guys have any training requirements, any training you'd like to do? I see a couple of people came in late. I'm going to go back to the, let me just jump off the slide for a second. So if you have a cell phone?
Yeah, I did.
Oh, you did? Okay, good. All right, cool. Just making sure everybody in the room is,
Hang on one second.
okay. Whoops.
I just walked in.
Yeah.
I found out about it like 40 minutes ago.
No problem.
All right, so thank you.
So good, 5G, that's a good one. Small cells. I don't know which MSOs you're working with, but small cells are going to be a big thing coming up here. I know because we make communication products that enable small cells on the HFC network. So a lot of you are going to be seeing a lot of those. Capacity, security, R5, that's good. Powering, I like that. Powering's getting a big following. I appreciate that. Whoops. And let me get rid of this little pop-up here. Let's see. All right. And now I'll go back. We'll go ahead and continue. Let's see. The next question is, whoop. I had one thing pop up that I'm not sure, you know what I need to do? Let me just get this off the screen. There we go. I don't need to have this open up anymore. How long have you worked in the cable network? We went through that one. And right now we're doing how long have you worked with HFC power supplies? And again with me, because of my background, I have worked with HFC power supplies since about 1994. So I'll go ahead and fill in mine. And that's good. Actually, I'm surprised. This is one of the first times that I've run into doing a presentation on this recently where there was actually a great deal of people with less than 5 years experience with powering. So I will hit some of the more low-level slides. Sorry to those of you who have more time in HFC powering. And then let me go ahead and click to the next slide. All right, here we go. Well, like I said, it's the one thing you learn after a while is engagement. And then we went through the training. Okay. So we're going to do, whoa, hello, back up, back up. There's a couple of things that just popped up on the slide, and that actually goes to the next question that I'm going to query the group with. What's the oldest alpha power supply in your system? So there's a lot here, right? The Alpha XM 3.0 was released very recently, like within the last 2 years. XM3 was before that, has a very long track record, I believe almost 10 years. The XM and XM2, this is, by the way, Alpha XM2. A lot of people have XM2s, and that's the oldest one. The XM is the old one that used us to have to slide the inverter in from the side. And then the AM series was the gray one that actually made a really interesting whine when it charged the batteries. That was probably the biggest thing about that. Ah, somebody has an AM. And there could be, I didn't bring in all of the other brands. I didn't want to have 27, lists here, but there's, Multi-Link, there's the Electro series, there's the PowerGuard, APC, Myers, TSP, all those. But I just wanted to find out. So a lot of XM2s. There may be a large amount of those. That'll be interesting to see. Okay, let me click on the next one. So here's a question, and this is probably, this will be widely handled, but what causes the most outages in an HFC plant? So this is the plant that is driving all of the nodes and amplifiers, if you have any left, in your cable plant. And I'll go ahead and put down my opinion. Okay, I need to catch up here. Make sure you hit submit. Okay, what causes the most outages? Commercial power, cut cable. Oh, this is good. That's really good. Digging, okay, power company. These are good answers. Pelco bulk power. We'll have to figure out what that one is later. I'll have to do some research on that one. But to be honest, one of the biggest outage cause is power outages, which can be related to power surging. Digging, fiber cuts, all that is a huge one. And another, pretty good example is the next slide that we'll bring up. This is a tap, right? We all know that taps are made out of cast aluminum. That is from a squirrel chew. What? Yes. Squirrels sharpen their teeth on our plant. They will eat through hardline, and that's what they did to a tap. Now, that was one very dedicated squirrel, and I don't know how much of his teeth he has left, but he did a number on that. So there's a lot of things you'll run into. This is another example of squirrel chew. They didn't like the aluminum so much, so they chewed through the batteries. This kind of stuff does happen. Again, a lot of these are courtesy of George Bosak, who's been in the industry 30 plus years.
That's awesome.
Get one of these?
Mm-hmm.
Very hard to service, right? It's called the New Paul. This does happen. Like I said, he's a great guy for that. And this is the result of different things ending up in the power supply cabinet. And this is a little friendly guy poking his little face out. It does happen. They're nice and warm in the winter. You should start to see that pretty soon. This is what they do inside of it. They make nests. And then corrosion and other things, can get in there. There's a lot of different things here. But let me jump out again, back to the next question. How often is, well, that's not exactly the one I wanted to go to. What's the strangest power supply intruder you have experienced? Okay, so I showed pictures of different burn-in, in mine, go through. And I'm going through mine as well. So bees are a big one. How about fire ants? I got ants here. All right, somebody type that. And like I said, yeah, there we go. I was waiting for that one. Snakes. So mice are getting bigger. I'm surprised nobody put down squirrels. I think it's because it's too hard for them to get into the cabinet. There's not a big enough hole. But if somebody leaves that little connection for the generator on the outside open. Lizard, okay, and an SPI, wow. Now that was a very dedicated lizard to get inside there. The thing is there's a lot of stuff that that's out there. And thank you all for making that contribution. So let's see, we got that one done. What's the worst power? So what's the worst power supply? Cabinet intruder. We could do that. Normally, if there's hundreds of people, this is a good one. Let's put in one of my worst is a wasp. They always affect me a lot. I don't like mice, and I don't like bees. Bees are the worst. I'll go ahead and back you guys up on that. So this stuff is real, right? This is what we have to deal with every day. So the one thing is there is a power supply routine maintenance document out there. It's called the SCTE 205-2014 Power Supply Maintenance Document. And one of the things it goes through is looking for vermin and stuff like that. And I'll be honest, we try to mitigate that. If you guys are doing any ground mount cabinets like a PN4, one of the things that we suggest is to put 30-year felt down underneath. So you put down either your precast pad or your formed pad, and the first thing you do is put down that underlayment to try to keep little creatures from coming up. And the thing about a snake is you generally don't end up with one snake, you generally end up with 100 snakes. I don't know why. I can't find it, but I had a picture of garter snakes, and just like the entire bottom of the cabinet was filled with garter snakes. When you see the back moving, it just really freaks you out. Okay, so like I said, just wanted to hit a couple of these and go through them. Okay, so go ahead. This is another example of something that happened to a power supply. This one obviously caught fire. It doesn't happen a lot, but it can happen. And you know, this is sometimes when you go out to a power supply, you'll see something like this. This is another one that won't provide any backup. I mean, effectively the lead is pretty much corroded off on that one. This is one that also was either chewed, I think it was chewed, or exploded. That's another thing. Lead acid batteries are highly explosive if they've recently been charged. And other things that happen are like this, intruders. So you sometimes go to a power supply and there's no power supply, there's no batteries. That's a huge problem in South America. They have a lot of theft as well. This one, you can see everything looks pretty good on it. They're attached to it. And then this cable right here, the communication cable is run out of the outside of the unit. That one, somebody left the cover off of it, or tried to get in through the top cover. So remember, when we're working with batteries, follow the safety policies. Use the measuring and powering equipment that you need to. Remember, you need your gloves, which, nice part about this room, I've got all this stuff here. Now this is an electrical safety glove. A chemical safety glove also is probably a better thing to use since that has to be qualified. But your electrical safety and chemical safety gloves, your face shields, goggles, hard hat. I don't know about you, but in working in cable, there have been many times, again, South America, where I've been working on an amplifier or node, and my hard hat was banging on the secondaries. You know, so the lines that go pole to pole to provide the power to the homes, my hard hat was bouncing off of those. If they'd been open, could have been a bad deal. From a tools perspective, always use safety tools. Use coated tools that will not provide a spark. For some reason, we just provided as little space as we could in the bottom of that cabinet to work on those batteries. Now you can pull them out if you've got a slide-out drawer, but an insulated wrench and a socket set is always good. A blower is good. A blower is good for two reasons. One is to blow out the cabinet, part of the SCTE 205-2014. Make sure the cabinet is policed. But it's also good for chasing out mice and snakes and stuff like that from a distance. A DVM, good thing. A clamp meter. To be honest, get a DC clamp meter. It's hard to tell sometimes with a DC plant meter. Normally the best way to tell is there'll be a 0 button. But that will allow you to look at the battery load as well as the AC output. And then a Medtronic's meter, which we'll get into later in the unit. So real quick, basic AC/DC, right? So direct current, all the electrons move in one direction. Alternating current, they move back and forth. There's pros and cons to both of them. So DC is really good, but it's not very good for sending through a transformer. You really can't modify it. Whereas you can with AC, you can send it through a transformer and step up or step down. Another thing is corrosion. If you have a DC circuit, actually DCs will create more of a galvanic corrosion than an AC will. Again, advantages of DC, it can easily be stored. It has no frequency, therefore it's not affected by skin effect. What skin effect is in a wire, especially coaxial cable, the electrons tend to flow more toward the outside of the cable the higher the frequency is. So DC actually uses the whole cable, not just the outside. EMI is limited in DC. It doesn't emit a lot of things. And induction is not an issue with DC. DC voltage and current are constant. Semiconductors require DC. If you run AC into your cell phone, it's not going to end well. But DC will work fine. The disadvantages is it can't be used with a transformer. It is more corrosive, that galvanic corrosion we talked about. Generators and motors are more complex. And an HFC DC is used for actives as stored energy in the commercial. Advantages of AC, transformers can easily step up and step down, just like the XM3 is doing back there. AC generators and motors are more complex or less complex because they have effectively just a ring sleeve brush. Our power grid is configured to use AC and is less corrosive, but it cannot be stored easily. Now, if you have a flywheel storage system, yes, you can take an AC generation and generate and run a flywheel at a high speed, but we're talking about that kind of storage. EMI induction can be an issue. It does have a skin effect. It cannot be used directly with semiconductors. Voltage and current vary constantly, and it's still out, but effectively it is more dangerous than DC. In HFC, AC is used mainly as a way to transport through coaxial cable. We're using an NESC standard, which says that if you send a AC voltage out less than 90 volts AC, you do not have to have an electrical license to work on it. That's actually the reason we came up with that number. And that's the reason the newer power supplies put out 89. We're getting as much as we can, but as much as we can. Now, I'm going to talk about something called root mean squared. How many of you know what RMS means? Okay, it's the effective energy in an AC waveform. So you have the peak voltage, which is the highest the AC waveform goes. Then you have peak to peak, which is the delta between the two of those. But the important part is, if you take this waveform and you take it across the entire time, there's effectively a lot of times where there's no energy. This is the zero crossing point. So you go beyond the higher point and back down, but what RMS is a usable energy within that. So to get an equivalent of 120 volts DC, you need an AC voltage with a peak of 170. So we'll go through. Let me go ahead. So this is the DC equivalent of that AC waveform when it's rectified, filtered, and such. So Ohm's law, Watt's law, they both apply all the time. So it's E equals I times R, or W equals E times I, right? So this pattern here, the middle, is effectively all of them. So we have voltage, current, resistance, and power, and then these are all of the relationships to get from one to another. So for AC circuits, Ohm's law can only be used in purely resistive circuits because there's something called impedance that kicks in there. But we'll talk about that a little bit further in the presentation. So when you start to look at an AC waveform, right? If I had a tap here, which there are taps on that wall, and trust me, I wanted to take one off. There are components inside there that allow me to separate the RF from the power. We're using that same thing. This is how we use this function of AC. So we have inductors, capacitors, reactants, and impedance. And with this, we can build circuits that allow us to filter it out. And the relationship between these different items, Eli the Iceman. So we have the inductance and the capacitance working together. And like I said, I'm trying to get through this quickly. HFC, voltage and current, electrons moving through, create heat, increase the number of electrons, increases the heat. Too much heat will cause a resistor to fail, causing a short or open. The coaxial cable portion of the HFC is rated at 15 amps. I get questions all the time. I need a 918. I need a 921. I need a XM2 924, effectively a 24 amp power supply. Problem is, we can generate it, we can couple it, but the HFC plant isn't designed for that. The SK or the KS connectors, 5/8 pins, those pins are not designed for much more than 15 amps, and you will end up, in most cases, causing problems. So generally, when we have a higher current power supply, we will split the output at the power supply. And we'll send it in two different directions. So again, it's rated at 15 amps. The voltage on the cable plant is either 60, 72, or 89. 72 is pretty much not available anymore. The 60 or 63 volts, that's used a lot inside buildings. So the NESC is what we play with when we're outside plant. The NEC is what we play with when we're inside a house. One of the advantages of working for Enersys, I was recently assigned to the renewables line. I went through, did a lot of training, and I am a North American Board of Certified Energy Practitioners, PVA. So I had to study the NEC, and it's a very different code book than the NESC. Trust me, you like the NESC, you like outside. It's a whole lot easier to work with. So when we look at utility power, right, there's a generator. Normally it's hydro, or it's created by the burning of fuels, driving a turbine, creating a generation. That generation is then stepped up from about 30 kilovolts to 500 kilovolts. Now these are the very large transmission lines, the ones that are hundreds of feet in the air. And you can generally tell by the size of the insulator. It takes like a 7-foot insulator for these. They don't look that big, but if you took them off, those things are huge. That carries it out. We then break it back down from 500 kV to a regional. This would be like a substation. And then finally a smaller substation, or could be an integrated transformer, to break it down to between 7.2 and 16 kV. Then it reaches the outside of your house or the outside of your power supply, and it gets converted to what they call low voltage, which is 120/240. We don't call that low voltage. So it's pretty simple. And we'll just go through. So this is typical transformer, looking at 7.2 to 16 kV. And by the way, every different utility has different powering on that side of the transformer. It's that they all are very custom in a lot of ways. This is outputting 3 connections, right? So we have a neutral, we have a line 1, and a line 2. So there are 2. The difference between these two is 120/60. The difference between these two is 120/60. But if I put them together, I end up with 240. So at most drops, you have 240 volts. It's divided out in the panel or in the sub-panel and broken out that way. So power disturbances are classified in various categories depending on the nature of the interruption. So interruption is a kind of a global term, complete loss of AC for 30 cycles or longer. Now, I don't know if anybody knows the new CCAP. You guys know what CCAP nodes are, right? Where you distribute part of a CMTS out in the field, either an edge plumb or possibly more of the CMTS. In that architecture, there's another thing. So rather than 30, it's 3. 3 cycles will cost you 15 minutes. That's because if your power is interrupted for 3 cycles, those CPUs within those units will shut down, and it takes them up to 15 minutes to come back up, and that's not including how long it takes for all the other cable modems to come up. So this is good for the powering for us. We handle that just fine. Transients are temporary rapid fluctuations in the measured quality of total power. And the reason I'm reading these is I want to be accurate. Surges occur when the voltage is 110% above what is considered normal. Now, transformers can be output different things, and just like us, different sites will have different normals. But when it goes 110% above, it is considered a surge. Spikes occurs when there's a sudden voltage peak, and it can be up to 6,000 volts. This happens during a grid switch. And sometimes I have fun. I'll bring in a transformer, and I'll bring in a D-cell battery. And I'll have somebody hold on the lines, and I'll disconnect the D-cell battery. And it will collapse. When it collapses, it actually can surge, kind of like the way you fire a spark plug. So that gives you an idea of the amount of surge you get out of it. That's effectively where these spikes occur. SAGs are short-term cases of undervoltage where the voltage exceeds the allowable threshold for 60 milliseconds, and then brownout is when you have a utility response, and effectively it's in excess of 3 to 5%, and the whole plant will go down a voltage. Whoop, sorry. Sometimes this thing does that. Okay, back. There we go. Okay. In a standby power supply, transfer remains to batteries controlled by a circuit called the AC detect circuit. So in every one of those alphas, there's an AC detect circuit, and it will follow the voltage, like in most cases, 60 hertz plus or minus 3, then an amplitude from 90 to 138, and from 173 to 276. As long as your power supply, your 120 volt battery, stays between these numbers, it'll stay online. Now, our field devices don't really care about what the AC frequency is, so that's not a big deal. And they'll operate through this, and the power supplies actually are a tapped transformer, so it'll regulate the output, and the ferro also helps with that regulation. And then make sure there's no distortion in the waveform. If you stick a generator on the front of a power supply, if that generator is dirty, that will never connect to it. So you have to have a good regulator, good brushes, everything has to be good in that generator. The input waveform is important due to the design of the transfer circuit. Circuit breakers, I saw one laying over here somewhere. Maybe it's on the other table. But circuit breakers are important. You cannot put a standard circuit breaker to drive one of these. We have a very high inrush current. You have to charge a tank circuit. It's a 60 hertz tank circuit. It's why we call it a ferro. A ferro runs a tuned circuit. If you can imagine somebody hitting a key on a guitar, we tune that circuit. We tune it to 60 hertz. Because of that, we need a high magnetic breaker. And this is an example of a single pole and a double pole. Again, what you're looking for is an HACR breaker. But it's a high inrush breaker. Okay, talking about connections. Now the one thing is, if you notice, my XM3 is plugged in over there. That's because that outlet is a 20 amp. That outlet's a 20 amp. How quickly can I look at that? This is a 15 amp outlet. This is the one you normally see in your home. This is one you get from Home Depot. Okay? You can get one of these. It will normally be in like your utility closet or something like that, a 20 amp. Most of our XM3 power supplies are going to use this 120 20 amp. The other you can do by using a divided blade is this 240. Now this one, if you plug in, let's say this one into this one, it's no problem, right? I can't plug this one into that one unless I bend the terminal. I don't want you to bend the terminals. There's a reason, right? Higher current demand. But if I plug this one into this one, it is not going to end off the power supply. Okay? So make sure that you know it. And by the way, the other end of that cord is identical in all alpha power supplies. So the XM3, if you take a 220 cord, you can plug it into a 120, no problem. So talking about surges and suppressors, these are some different examples of surge control. What a surge is, again, it's just a quick spike, and it can be up to 6,000 volts. And this is kind of a map showing you where all of these types of surges can happen. Okay. So you probably never looked at this, but this is the way that power gets from here, from the utility, through to the front end of our power supply, either 120 or 240. Then inside here, there's a ferroresonant transformer. That's the tank circuit, right? So we output 63 or 89 volts in this, what we call a trapezoidal wave or quasi-square wave. The interesting part is, because of the sinusoidal nature, this has 0.707 captured energy. So when you look at your RMS versus your peak, it's 0.707. or way higher than that. Depending on the power supply, it can be up in the 90s. But what we're doing is we're creating more energy delivered at the peak. So there's actually there's a lot of energy in here versus what it would look like if the same voltage in a sinusoidal was represented. And then finally, that comes out of here, goes into a power inserter, and using a frequency method, it's combined and isolated from the RF that's traveling through the plant. And then finally, once it reaches these devices or sub-regulators, they convert it into effectively pulse DC and then filter it into constant DC and run all the electronics. That's how your plant works. Power inserter. So there's one over there, I think on the floor or something, but what a power inserter does is that there's a filter circuit. And effectively it's more complicated than this, but effectively it's an inductive circuit that only allows the power to go through in this direction. This direction won't handle power and RF. Now the one thing that's missing on this is the additional shunting fuses that allow you to control which direction that goes in. So when you put it up like this is the RF path, forward and return. It only goes up to here and then it's blocked. So the power supply does not affect this at all. This same technique we're going to talk about later when we start to talk about plant design. When you effectively start to deploy node +1 or RFI nodes, you're going to use these back to back to allow power to transfer, but to isolate two node circuits. So it's the same kind of a device. And this is not a very shocked HSE component. This is a representation. Sorry, that's what it kind of looks like to me. This is a tap. And what a tap does is it allows to pass AC. And again, there are likely going to be power shunts in here, jumpers that allow you to send or not send power. And then capacitively, it isolates this. Now there's another device called a power passing tap, which can tap into this and through another circuit add that power back into this. And when you start talking about small cells, that's where you'll use that. Inside an amplifier, the power is broken out at the edge. There's a diplexer, a frequency diplexer, that splits off the power and the RF, and then there's a second diplexer that splits off the forward and return path. So the forward goes through. This is just a very simple amplifier. The line comes through with all energy. The power is split off. It's run through fuses and circuits that allow it to go out of different ports. It is taken off, so they tap into it. They create 24 volts, which drives all the electronics. And then separately, the forward is equalized, amplified, equalized, tailored, and sent out this way. The return's brought in, amplified, equalized, and sent back to the head end. So when you start looking at the way all of these different things pass, the one thing not shown here is the DC. But effectively, all this is happening, and it's all frequency diverse. The power comes in from the plant. This is a breakdown of the actual electrical circuit. It comes in, it's stepped down, possibly. This is old technology. The new technology, it's a switching regulator, but it's rectified. This is a full wave bridge rectifier. Comes in as a DC raw, then it's filtered, and it ends up looking like this toward the end, which allows it to be used for the amplification. So now talking about power supplies. And this probably is where I should put in the other power supply slide. XM3, there's an XM3.1, couldn't fit it on the slide. XM2, XM1, XM series, the slide out, actually it's on that side, slide inverter, AM series, and this is an earlier version of a non-standby ferro. So the non-standby ferro does the same thing. Again, there's different brands and stuff. It's effectively just a ferro, which is a transformer with an isolated load winding and a capacitor that creates the 90 volts. No standby with this. It does do some limited line voltage regulation because of the way the ferro works. It's often not used in voice service because there's no standby. 911, as soon as you add that, you have to add batteries. There's no intelligence, no status monitoring. Try one more time. So this is a standby with UPS. Again, it has the same ferroresonant transformer. It has batteries now and an inverter section, inverter charger. It provides uninterruptible power. It's optionally used for providing voice. It provides status monitoring, intelligence, and it has self-test capability. I'm gonna pass this around. Try to be careful with it because this is actually one out of a working power supply. But this isn't the inverter, but this is the intelligence stack. So that has the you can see the SAG on the top of that. There's different forms of communication inside that. So has anybody in here worked with a transponder? That's the XM3.1's version of a transponder. You can see the heatsink on it. It does a whole lot more than a transponder does. So when we start to look at how things break out, again, what you're looking at over there is more or less the embedded DOCSIS transponder section. But effectively, you have your input. There's a surge protection circuit here. This is a very important thing. It's called the line isolation relay or isolation relay. This is what makes it so that we can run a UPS on the AC power line. If that fails, so if you have an alarm for a line isolation relay failure, you need to fix it immediately. Because now, if this power supply goes offline, this inverter over here will use the batteries to create energy for the AC plant, for the HSC plant. With that relay open, that's all it does. If that relay failed, that energy would go back out of that plug, which, okay, so it's 240 volts, how bad is that? Until it hits the transformer. Then it's 7.2 or 16K that these guys are working on the AC lines on. So you definitely want to make sure that if you get a line isolation relay, you get that addressed quickly. So along with being able to create that power and set it this direction, the inverter should say a charger underneath it. It also sends power out to the batteries. And there's a temperature sensor and some other items for doing different things like that. This is a ferroresonant transformer. This is the actual, just a simplest circuit. So it's got a transformer. Normally there's split windings on it. It has a capacitor. It acts as a standalone line conditioner. In a fold-out condition, it can output 150% its output rating. So again, why do I need a 50 amp power supply when it actually can put out 150% when it needs to? Current limit, again, this will reduce current. It'll fold back. So one of the other things is if you short one of these, it normally just goes into a fold-back mode. It keeps running. This provides 1,000 to 1 attenuation against voltage spikes. Okay? So if I get a voltage spike in, it's cut down. Now to put that into, when you look at 1,000, right? 10 is 10 dB, 100 is 20 dB, 1,000 is 30 dB. So to put it on the RF scale, that's a 30 dB attenuation of that signal. And it's just because of that circuit. So it's kind of cool. The inverter section, effectively it's an H-bridge, really simple. It allows us to invert and charge using the same electronics. It does use FETs. These FETs actually do have protection in them, even thermal protection. So everything is monitored within the system. There's an AC detection circuit. One thing that's important is, what is the voltage of the system? If you take a 48 volt inverter and you slide it into a 36 volt power supply, it's not going to work. And if you do it the other way, into a 48 volt, things are not going to end well. So, you know, does it need a fan? Different things like that. There's a lot of considerations there. And again, looking here, power's going through, charger's on, batteries are getting charged, plant's running, normal operation mode. In standby mode, DC goes back out, it goes through, this H-bridge actually kind of sends it back through. Should be a sinusoidal wave, should be trapezoidal, but it comes out like this. And then status monitoring, again, that's part of what that card had on it. It provides remote monitoring, preventative maintenance. It's visible to the NOC, XSE, TOC, provides all of these different measurements, and then all of these different items are required for it to talk. So there are LEDs on the front of this when you're hooking it up. If an RX is between this, green light. TX is between this, green light. If it's outside of this, it begins, you get a blue light, and then you get a red light. And red light means you can't really talk. And then we need SNRs, just like cable modems do. And it will It will do bonding in the DOCSIS 3 or DOCSIS 3.1. And then you always want to make sure you ground the RF connector on it. Again, looking at the way this goes, the power supply will have a drop connected into a tap. Now, if you have a directional coupler and an SPI RF, that wire can go there, it'll go through here and end up in the plant because there's a diplexer inside that. It then gets inserted, it gets changed to optical, and then goes back up through the CMTS, and then it's available to be presented. This is how Power Supply Notebook works. This is how Continuity and XD work from Alpha Products. So there's a lot of different alarms you can get. Self-test fail, line isolation, again, that's a really bad one. No batteries, inverter failure, output current, output voltage, input voltage, line standby, RX and TX levels. I'll go into more detail on this. The ones that are important, line isolation. Again, relay's bad or something, let's take a look at that one. Self-test fail means that the unit went into either a manual or automated self-test, which means it went to the batteries and expected to run for a certain amount of time. Something interrupted that. Could be bad batteries. If you get one of those, whoops, sorry, going backwards again. If you get one of those, reissue it. Actually go into the software and issue a self-test, let it run for 10 minutes, shut it off. Sometimes that'll clear. Because what's the power supply's primary purpose? To provide power for the HFC plant. If it's running its little happy standby event and the AC gets interrupted, it goes, huh? And will immediately go back to AC if it's available. Because it's like, the power grid is now unstable and I need to make sure that I have all the battery I can have. If you're in the middle of the self-test fail, what is where's this battery? Sorry guys. Let me go down to, I don't know what just happened. He just went home. This will give you an idea how many slides I've gone through today. Getting close. Okay. I want to talk about more on this a little bit because I have one section on that. Okay, batteries. You don't want your batteries to look like this, right? Most HFC powering is powered currently by lead acid batteries, LA batteries. Now, they can be like these. These are actually called valve-regulated lead acid batteries. So any sealed battery is valve-regulated. So inside here, there's a circuit. And when I say circuit, it's not electrical. It's actually a mechanical venting circuit, which allows the batteries to outgas if they need to, but it's regulated. So they're sealed for all practical purposes. Again, before working on batteries, observe all safety. I'm not wearing my right alpha shirt. I have one that I have a nice little burn hole in my elbow where I laid it on a battery as I was working on it. And the next time I washed it, I no longer had an elbow because the acid had eaten it out. So be careful, wear gloves, wear sleeves if you have to. Remove all jewelry, wear a face shield, chest shield and such. Lead acid batteries experience self-discharge. This is one of the issues with lead acid batteries. If you don't charge them, they will actually self-discharge. They have a very high current delivery, and with that, they self-discharge very well. All batteries should be fully charged before they're put in storage. Store in a clean, dry, well-ventilated area, 32 to 68 degrees. Batteries discharge at a slower rate, hence the reason. Don't freeze them, but don't get them too hot either. If the voltage is less than 12.6 standing, the battery needs to be charged. You should, batteries sitting for 6 months should also be recharged. There are some newer technologies which HEM and such say if they provide longer periods. If you recharge 6 months, you'll never have a problem. All 12-volt batteries are not created equal. There's wet cells, kind of like golf cart batteries, gel cells, and AGM. Two primary types of VRLA, valve-regulated lead acid, are gel cells and AGM. AGM and gel cells are both non-spillable, maintenance-free. All 12-volt batteries, so the electrical circuit in a battery is called a cell. It is created by lead plates and lead sponge and sulfuric acid in a dilute form for the electrolyte. Each cell produces 2.2 volts. You stack 6 of them together, you end up with a 12-volt battery. So some batteries may be larger than others. Some may be designed for deep cycle circuits, deep cycle or float discharge. Some batteries are designed to be cycled, like a renewable energy battery, but it may not have the efficiency that a regular battery does. Other batteries are designed to be in a float mode, which means I'm here, I'm ready to take a discharge. But if you do that to me every day, I'm going to fail on you. So you have to make sure your battery's the right design. To be honest, we're a standby, so a float charge is perfect for us. Batteries last longer in cooler environments, but they don't do well below 32 degrees Fahrenheit. So they lose energy, the capability of delivering energy as they get colder. Do not have batteries cable connected to the power supply when connecting the batteries. Do not have the battery cables connected to the power supplies when connecting the batteries. Sorry, I had to say that again. In other words, don't connect these up until all of these have been done. Do that one last. Ensure you have a minimum of 1/2 inch spacing between the batteries. Positive terminal should be toward the front of the enclosure. Because you have more positive, there's more potential of energy delivery from a positive than from, let's say, this battery negative. And normally, number 1 is the farthest right. A1, A2, A3. If we have a second set, it's B1, B2, B3. Third set, C1, C2, you get the idea. Now the interesting part is, this is normally the battery that fails. Why? Because it gets hotter. Because when all the batteries heat up, these two are cooling to the outside of the cabinet. This one can't. So it actually, from my experience, which again I've done this since like 1994, that happens. So batteries can be connected. This is a 48 volt string. Simple enough, I just add in one more battery. And I can also do a parallel arrangement. The thing in batteries in parallel, check with the battery manufacturer, but rule of thumb is 3 in parallel max, okay? Some battery manufacturers will do more. We have batteries that we can stack 4. The reason for that is that we need to balance these. Because if you don't balance them, a weak battery will take out the rest, right? Speaking of a balancer, we have a device called a SAG. That's what on this device is the white connector. On the XM3.1, it's on the side. That's this device here, right? This connection. This is a function. You can see all the relays and different things that are happening inside this. But what it does is it notices any difference in the battery's charging, and it will adjust the power delivered to the batteries as it needs to. One last item is a temperature sensor. There are 2 temperature sensors that Alpha has used throughout the years. One is designed to go between the batteries. That's a temperature probe. Then there's a PTS, a precision temperature probe, which gets attached to the negative line on cell 2 to monitor the batteries. Now, why do we need this? In order to charge a lead-acid battery, there is a temperature variant. It's 5 millivolts per degree C per cell. It's the standard lead-acid. It can be as small as 0.2, as much as 0.5. But what that does is, as the temperature gets colder, I have to jack the voltage up on the charger to get any electrons to flow into the battery. In other words, it's hard to move those things through that cold liquid. Think of it like Jell-O. It's not Jell-O, but as it gets colder, it's harder to move. It gets warm, really easy to move. In the cold winters that you guys up here, right? You ever reach like minus 40? I've seen minus 30, minus 40 with a 16 volt charge to get the batteries to take a charge. So it's not a problem, it's a reality. But that's part of it. Battery cable attachments, again, ensure the post cables are clean and free of corrosion. You do not want them to look like this. Ensure the cables are properly connected, properly tightened. This is a top terminal battery, right? But this has the tab on it. I don't really care how long that screw is in this scenario. This is the same top terminal, but this one goes into the battery. There is a depth to this. Use the right bolt. If you use the wrong bolt, it will get really hard to tighten at the end, but you can keep tightening it, and what you'll do is you'll shove that thing right into the battery itself, and things will not end well. Most of the time it just breaks it. Sometimes I've seen it actually go far enough down to cause other damage. Oh, don't do that to me again. How do you like my, we're almost there. Okay. Uh-oh. You gotta hate this. The thing's taking me in two different directions. Okay. So again, not all batteries are created equal. I think I went through this one, right, didn't I? Yep, half-inch spacing, yep. Yep. Okay. Now we go. Battery charging. It's best to use batteries that come out of the box at 100%. I'll tell you, if you go to Sears, sorry, Sears isn't around anymore. Okay, you can tell how long I've been doing this, right? If you go to Walmart and you buy a battery off the tray, if you take that battery and you charge it up at home, you will actually have a longer service life than if you just plug it in your car and start it up. If you trickle charge it, it'll actually improve the battery lifetime. The last battery I put in my car was it's a platinum battery of some sort, Craftsman platinum battery. It lasted me 8 years in my car. That is a very long time for a battery. It's because I charge it up, and routinely I would trickle charge the battery to full charge. It was an AGM. But again, bring them out of the box. Temperature sensor is important, critical actually. Most power supplies will adjust based on the temperature, which I went through. Warmer temperature, lower battery, higher temperature, or lower temperature, higher voltage, higher temperature, lower voltage. There are also different charge modes depending on the type of battery. Bulk. What a bulk charge is a constant current mode. In most alpha power supplies, that's 10 amps. So what this does is this is actually bringing the ions in as fast as it can and delivers them to the plates, moving all of the stuff. Once the plates have kind of reached a full voltage, then the voltage or the current will drop off. This is called the absorb or the accept. In every other industry outside of cable, it's called absorb. In our industry, it's called accept. That's a constant voltage charge, and effectively it'll trickle down until you reach what's called the end of charge, the EOC, which is generally about 2% of the charging current, blah, blah, blah. Then at that point, depending on the type of battery, if it's lithium ion, that's normally your charge cycle. If it's lead acid, you may have a refresh, a float, a rest. The ones that are typical in most lead acid are bulk, accept, float. AGM, or some of the newer AGMs, you'll have a refresh, a rest cycle, and then a float and rest at a regular interval. I'm going to get very much upset with this thing. I don't know if it's something strange there. Okay. Okay, let me get back. We're almost there. Battery balancer, I think I went through this pretty well. Ensures battery life potential. That's the biggest part right there. It allows replacement of individual batteries instead of a string replacement. It reduces the battery preventive maintenance. It allows you early visibility into weak batteries. Again, end of discharge, I talked about this too. It's normally 1.75 volts per cell, which works out to 10.5 volts per battery, and for us, it's normally about 31.5 volts for the string. Fully charged batteries measuring less than 12.6 volts should be replaced. These are ones that have been put in the field, have been fully charged, and then they turn out to be that voltage, replace them. Battery runtime is dependent on transformer efficiency, output load. So just to put it in the most important thing, output time is dependent on output load and the size of the batteries, effectively. But when you break it down into these other things, environmental conditions, a system that will give you 4 hours of standby in the summer may only give you an hour of standby in the winter because of the difference in temperature. So things like that can happen. Age of the batteries, as batteries age, they get used more, they corrode, the plates break down, things like that. Type of battery, again, depending on weather conditions, type of battery can be important. AGM works really well in the winter. Power supply preventative maintenance. Let's just go through this real quick. Again, this is what you want it to look like, not like that. Generally, look at this as a before and after. So I'm going to jump back to the cell phone upgrade. Get out their cell phone. And what we're going to do is look at how often routine power supply maintenance is provided. And I need to forward my slide. And actually, I just have one slide here that's out of order. Which one is that? How often is routine? Yeah, there we go. Got it open. Go to slide. If you want to click the top of your screen, there's a little pop-up on your window. You just say go to slide. And now what I'll do, go to the other page. Okay, once every 6 months. That's actually what the SCTE recommended in the 2014 spec. And that's actually the one that I'm going to suggest. But the thing is, from my experience in other people, a lot of times it's only once a year. There's other places that only do it every few years. There's other people that are reactive and they only do it when the power supply monitoring system tells them they need to do it. Other people do it when they have an outage.
That's time.
It's not the time to do it. And then we don't use backup powering as another option. But it looks like everybody's riding it on 6 months, which is perfect. You can't ask for anything better than that.
It's supposed to be 6 months?
Yep,
Yeah.
it varies.
It used to be every 6 months, and they contracted it out for a while.
Yeah.
Right.
And then they kind of sandbagged it, and now it's back to 6 months. So, like, I'm not really sure how to answer that question.
Exactly.
Yeah.
It depends on the system, I think.
Okay.
The workload, the workers.
Got it. Got it. So let's just talk about doing it again. Remember your safety procedures. We went through a lot of this. Eye wash, skin wash, baking soda, things like that. And then effectively a way to collect the data. So a record, true RMS voltmeter, inductance meter, and that was one of my other questions that I'm going to pop up here. Probably is the next question. Well, no, not yet. We'll get it in a minute. But I want to know how many people use conductance meters. So SCTE 2014-205, this is kind of a really quick run through of what they want you to do. Physically inspect the cabinet, look at grounding and bonding, make sure the cabinet is clear, make sure that's a hornet nest right there on the side, make sure it's accessible, make sure that nothing is moved in, remove dirt, dust, and debris. On the power supply, there's a smart display and there's a test button. So part of the thing, you're going to have to test the batteries, check the strain voltage, check the individual batteries, make sure everything's good there. Physically inspect, again, make sure the battery connections are tight and the batteries are actually physically there. Individual battery test, conductance test. And that's the next question on my list is how many people have conductance? There we go. And I got it on. How do you test VRLA batteries? This is my shot here. Okay, using impedance meter. That's me.
That's just the way to
Okay, this is perfectly legitimate. I appreciate you guys answering this because impedance meters are not cheap, but it's the only physical way to look at the health of a VRLA battery. There's no other way. You can do a load test and a discharge test and kind of, yeah, well, that looks pretty good. But this is your fastest test. One time at a auto parts place, person came in and they brought in their battery, didn't know if it was good or not. You know, and it was, I could tell by the size of it, and I had my unit in the car and I just did a quick pop on it. You know, they were doing like a 2-hour discharge test and I just popped on and, you know, told them what the Siemens of the battery was. It was actually still good. So they had another problem in their car, it was the alternator or something. But That's good. We use load testers. That's very common. I've run into that a lot. And it's not just our industry, guys. Like I said, I worked with the renewables line. I worked with tons of solar installers. And you know, Comcast spends a lot of money on batteries. These guys spend a lot of money on batteries. There were sites that I visited that have well over $30,000 in batteries for their house. Okay? With that, we're providing 1,000 watts of output, right? Give or take. You run a house, it's a lot more. So these batteries, they got batteries the size of that refrigerator in their house. Batteries weigh 688 pounds apiece. It's crazy stuff, but it's good to know. It's good to know that there's some impedance testers out there. Okay. And next one. So again, move the inverter and inspect. Make sure that the breaker is working. After the self-test, shut off the AC utility breaker to test it. Replace the inverter if defective. The one thing I'll tell you is that when you do a power supply maintenance, what's the first thing you want to do? Bring in your backup power supply, right? Plug it into the auxiliary plug at the top of the SPI, and make sure that you are powering the plant by something reliable. Because during your test, you may cause an outage. If you flip that switch quickly, you won't violate the 3-cycle limit. Don't flip it slow, okay? Flip it fast, and you'll be able to ride through. You can do whatever you need to do to the system. But I'm a big one for that. Again, transponder, check the RX and TX levels, the mirror there, look for T3, T4 timeouts. Generators. Do you guys use generators?
Yes. Yes.
Should have had that question. Do you use this kind of generator, or do you use one that's actually physically mounted in the cabinet with an LP?
Little suitcase guys.
Suitcase guys?
Yeah.
Okay.
AC or DC.
DC. Okay. Very good. So again, with any of these, follow the operation. If you're not using gas or DC, just make sure make sure it's charged. Make sure you use the approved charger to charge it, because a lot of those might be lithium based. Don't skip on the chargers. AC curbside, this is what I was talking about, where you could have an alpha gen built into it, or a generator that's natural gas. How am I doing time-wise? Oh, we got half an hour.
Yeah.
Oh, dude. Now we're going to get into the fun stuff. Sorry about a whole lot of background with blah, blah, blah stuff, right? Now we get into some fun stuff. So, the HFC plant, believe it or not, has a lot of voltage loss throughout the system. Okay? When you start looking at where current is traveling, it's not just the 0.25 or 5 amps, it's what it all sums up to, right? And there's resistance on each one of these lines. So if you look, there's also a thing over here. This is a voltage versus current chart of a switching power supply. Remember I told you that one image was old school with the transformer in the front of it? So these devices will run from 90 volts down to about 45 volts. They will cut off at 45 not because they can't run lower, because the MSOs have said if you run lower than 45 volts, you'll create such a current draw that it would cause a problem for my powering circuit. Right? So when we add all these up, this device, let's see, a device that pulls like about a half an amp at 90 volts will pull 0.3 or 0.88 at 38 volts. And when you're looking at like a node or an RFI node, you're looking at like 2.1 amps. I'll just be honest, from my experience with the ones that I've used, and these are the big ones, you know. They're not this isn't like an LE, this is a big thing. So when you look at a long cascade in a 60 volt system, if you have like 2,500 feet, you might be generating 63 volts, but you can very quickly get down to 53 volts. That's because this is going to pull more current because, again, that voltage is dropped. My line resistance doesn't change. So let's just say I flip this to a 90 volt power supply. And by the way, these two are not going to work in this scenario. I flip it to, oh, don't you do that to me. I think I need to go back a couple more. There we go. Okay. So there we are. So again, this was my slide. Now I'm going to flip it to 90 volts, and now you see because they're drawing less current, and I have a higher voltage, we can easily power at the end of the plant. This is 60 volts. That's 90 volts. This is the reason that all the MSOs are moving to 90 volts. 89, yes, 89. So, so you're doing that to me. I have to get a new presenting mouse.
Sure you have.
Okay. So when you start to look at node plus X, right? Node plus X architectures, there are two ways to do it. One is to build it from the ground up as a node plus 0, node plus 1, node plus 2. Again, with 63 volts, you might have to have multiple power supplies. Look at the same thing on 90 volts. You can break it out. Now, remember I talked about the power inserters can be used to remove power? So if each one of these is an RFI node with a different RF setup, we can use the same physical connection infrastructure. So this is an RFI upgrade, right? A CCAP node upgrade. So the first node will be the same. What you'll do on the other node, using the same HFC wire, at some point in the plant, you're going to break that out and actually physically take the power, pass it. But now, rather than the RF going in this direction, it's actually going in that direction. So these taps you flip. But this is a simple upgrade to a node plus 0. And again, node plus 0, a 60 volt plant, got lots of power supplies. 90 volt plant, you don't. I wanted to talk a little bit about using your DVM on site. So the first thing you want to do before you ever touch this, and this is per like NEC rules, NESC rules, check this grounding conductor with a voltage. There's a voltage detection device. Those little things that scream when you get near AC voltage. It is possible that something happened in utility and this line is actually hot. So you want to make sure that line's hot. It should be bounded, and then this also would be hot. So use that as you need to. When you look at your AC outlet, you may see the same RMS reading out of a true RMS meter and an average meter, right? And the one thing that you want to see on it, and I wish this had it, is true RMS. So AC sinusoidal waveform, they'll measure identical, or relatively identical. But you look at the trapezoidal wave, that's the actual voltage in RMS. That's what it's thinking it is based on an average. Okay, way off. Invest in an RMS meter. And then when you look at the power supply and standby, same thing. We're outputting almost the identical voltage. We've changed the duty cycle. This is how we extend the battery life during discharge. So we don't always hit it with all the energy. We actually reduce the energy to produce the amount we need to power the plant. But again, a non-RMS meter won't measure correctly. Okay, here we go. How does this short in the HFC plant affect the XM 3.1? That's the unit that unit came out of. The reason I'm going to read this is actually pretty complicated. The power supply demonstrates the HFC XM 3.1 950 power supply. Note that the XM3 and the XM3.1 with standard outputs react in the same manner. So this is true of an XM3 or an XM3.1. In this example, the XM3.1 is powered off 120, but 240 is also available. The plant is connected via output port 1, and it's using a power inserter. So there's a the SPI and a power inserter. The power inserter is shunted as opposed to having fuses. So pretty much, in this case, the entire plant is shunted. There's no fuses in the plant. Okay. In this example, the left leg off the power supply has a 4.9 amp. The right one has an 8.7 amp draw. So though they're not shown, batteries and everything are connected. So what you'll see on the power supply is 89 volts. And again, that's my launch voltage, right? It's going to drop, but that's my launch voltage. At 13.6 amps, which is effectively those amps that are added up. Okay. Now, if somebody shorts something down here on this leg, right? Tree falls, car hits a pole, whatever. What will happen is it'll create a huge draw. And this draw is only limited by the resistance of all of the active components, passive components, and the HFC cable itself. But effectively, this is going to drive it to like 19.1 or 23 amps at 0 volts. So what it's doing, and it's not exactly 0, it'll be around 0, but 23.6 amps heading in this direction, okay? The ferroresonant transformer will fold back. Now physically, it physically goes into a state where it's just dissipating the current and running, but it's not delivering any power. The power drops to 0, but the output current rises significantly. The output remains at 123, but it actually does, it increases to try to provide all that power. The HFC Smart Display shows active alarms, so you'll see that there will be a power alarm on the unit. After 30 seconds of foldback, so effectively short, right? Power supply for 30 seconds will do its best to deliver. Then it's going to intelligently switch the HP inverter to open, which will disconnect the units from the transformer. So no draw, no output voltage, no output current. It physically, for all practical purposes, shuts itself off. Now it'll wait 1 minute, right? That's the reason I have to read this, because it's very timing centric. 30 seconds off, now it's off for a minute. After a minute's passed, it will do an intelligent problem. So what it's going to do, it will try it again, right? It'll turn it on, ping it, still sees a problem, shuts itself off. It'll continue these 1 minute output off periods for 20 times. Then, after 20 minutes and 1 minute, it will then begin to turn off for 30 minutes. So, for the first 30 seconds, it's on trying to run, then it goes into this pulse once a minute, just, testing things. And then after 20 minutes, it's once every 30 minutes. After 30 minutes, output off periods will continue until the problem's resolved, so it just keeps on chugging. While the XM3 is outputs off, if you remove the short disconnecting the connectors, or if you fix the short, the XM3.1 will not turn on until the output off period has completed. Mm-hmm. So if you go in and you fix it, you either need to go back and cycle the XM3.1, or you have to wait for the rest of that period to elapse before it goes and tries and turns itself back on again. To stop the outputs off period for current, shut off the XM3.1 battery breaker, connect the battery breakers from the inverter. So now we're going to go into test mode, right? To do test mode, we're going to shut off the breaker. With the intelligence mode, the XM3.1 will go back and will fold back due to the short, but it will no longer do the outputs off. So now I'm in diagnostic mode. I go up, shut off the battery breaker, the ferro kicks back in, and now I've got 23 amps at effectively 0 volts. So I'm dissipating energy through the plant. Now, when measuring it out, make sure, pull out the SPI, make sure the power supply is working normally. Okay, everything's fine. Then plug it back in, pull the faceplate off the power inserter. Now again, if you're doing this under power, you may get a small arc flash. So wear appropriate protection, right? Or goggles, because you don't know exactly what that is. But if you're working on it hot, go ahead, reconnect the SPI output, power inserter faceplate, using a true RMS meter, check the voltage on the input. Okay, looks good. Then test the current. So using a jumper, there'll be little tabs here that you connect a jumper wire to. This jumper wire needs to be at least a 12 gauge wire, by the way. Okay? Well, yeah, use a 24 gauge wire. It's going to end differently than what you want in this test, right? Use 12 gauge wire. Use a current meter, right? AC current's fine, but clamp it on, look at AC current, and you should see the draw. First draw is 8.7 amps per my plan. That's good. All right, that circuit's fine. Now we're going to check this one. This one goes to 23 amps, right? Which exceeds the draw from my plant. And now what I need to do is divide and conquer. I know now it's off the power inserter. It's something down this line. So then the next thing I would do is I would go through, remember, power inserter, down the line, pull off the next one, figure out if I have, when I pulled off the face, do I have power there? And you just go through and keep doing it. Now, the one thing he did not show, I would have dropped the node face first and checked inside the node. There are devices you can get that will allow you to extend those, mostly use the MDL plugs out of like they look like car fuses. They make extenders for those. So you can bring the extender out, bring it out, put your clamp across it, check it in the node. Maybe there's something short in the node. This happens. But pull it off and just keep walking through the plant. And then we know here that it wasn't on that leg, it's actually on this leg. And then we can go in, once we fix it, then we turn on the battery breaker, everything's back to normal. You want to make sure that your systems are grounded and bonded. I have a little bit of problem with this drawing. These are 8-foot ground rods, right? No problem. But I would put them 16 feet apart. Normally, it's twice the distance of the rod to remove the area of influence. This needs to be a 2 AWG, 2-aught. This is a big wire that's going to connect these, and these have to be effectively welded in place. You can't just use clamps; you have to use welds when you're doing a bonded ring like that. And then again, when you want to check it, make sure it meets code. Get out either your drop meter or your impedance meter. You need 23 ohms or less. Again, there's tons of additional references online that you can go through. A couple of differences between that. You don't have a 3.1 here, so I brought up a picture to talk about it. This is the Alpha XM 3.1 low power version. This is a mini node. This is effectively one that might go in a building, things like that. This is a 12-volt battery. Okay, so it's just a tiny little power supply. It delivers enough current for like a single device, but effectively it has the apps built into it that can be turned on through software. It has the same Faro that everything has. It has an auxiliary output. This is unique to any powering device that we make. So in case you wanted to monitor this or you needed to drive like a cable modem, you can plug in the cable modem there, provide 120 volts that's backed up by the battery. So a switch, something like that you might need on site. It has 2 outputs. They're put in with small screwdrivers. External voltage selection is right there. Effectively just loosen up the screw, move it to the other voltage. It has had the same type of inverter, so it's very intelligent. Battery management, just like all the other XM power supplies. Smart display, and then it has the SFP monitoring. This is the same thing. This could be a 909, a 918, but it has the alpha app, same thing, pretty much built in. The difference is that card that I passed around. So how many of you guys are starting to do optical, like PON networks? You guys doing PON yet?
We have some, but not much.
So are you using like a Calyx or a Nokia OLT? Or am I just like...
You're so far over my head. I mean,
Okay. So they make OLTs that run on 90 volts. They look a lot like these.
You actually use them.
Yeah.
There's a variant of one of those up there. That's what we use.
Correct.
Yeah.
So that provides a PON network, passive optical network. The problem with that is there's no DOCSIS in a passive optical network. So what we did in the XM 3.1, we put in an SFP also.
Oh.
So we have a DOCSIS connector, and we can either use a copper SFP off of the ONUs you might be using for the home, or they make ONUs on a stick, which are optical in, so they plug right in, so now we can work through PON too. Now, there's an entire, like, 2.5-hour presentation on how to make all this work. I'm not going to go through all that. There's a lot of steps. But that's probably one of the bigger differentiators. So let me click on the next slide. And we'll get rid of that. Just give you a blow up so the people at home can see what I'm talking about there. And actually that's slightly off. It's right above it. So right here, this kind of shows you the way that you would connect it. That's an ONT on the stick. So effectively, does not support SFP plus, XSFP, only SFP. So you need to have units that are less than 2 watts or our back plane can't support it. And it'll just effectively fold back. It won't hurt it, but it won't work. Okay, gotcha. You are definitely going in the trash when I get home. Okay. So there's lots of different PON networks out there. This will work on pretty much any PON network with the correct ONU or ONU with a copper interface. Point-to-point connections can also be done through dark fiber out-of-band channels, copper SFP, and then you can also, because you can use a copper SFP, you can backhaul it over a cellular modem, a Wi-Fi bridge, satellite communication, DSLs, whatever you want to do with it. Again, I'm not going to go into this in detail. This is a DOCSIS transponder coming online. These are all the background processes that happen. And I'll walk through it. So, DOCSIS negotiation, downstream, lock, level, upstream, lock, level, all my parameters, everything works. Get an address, get a config file, get the current time, then talk to the management server, and then go online and allow communication. When you start to drop it into a network, there's different places you can drop it off of. Again, you can do it off of DMUX. You can do it off of an OLT using an SFP, or at the end of line using an ONU or ONT with an SFP adapter or a copper adapter. And it works a lot. PON configuration, don't worry about that. Get an IP address, get the current time, get the config file, talk to the management server, and it does not support connection to other devices. One thing I wanted to show you right here, CPE private. Most of the times I've actually worked in PON networks, this is public. So be aware, talk to your IT department, or they'll be talking to you because that's going to get a public address. And then this is just the same thing without PON, the way that we make it work. So that's it. And I think I made it very quickly. I'm getting a call from an unknown. I'm not answering that. So, any questions?
Yeah, I got a question.
Sure.
XM3 on the second string battery, there's only 2 leads, and I was always told it's because of the new technology. What's the deal with that?
All right, so that's a perfect question, and let me bring up a slide to show you why.
I mean, it seems to work fine, but...
It does, but I'll show you why. It's actually, when you see it, you're going to go, oh, okay, that makes sense. But without seeing, I appreciate you guys, by the way. You dealt with me talking to you for an hour plus.
I like that little interaction thing.
But you know what? I'm trying to get.
I don't know how you did that, but that's pretty sweet.
I want your input, and it helps. It helps everybody else too.
Tell whoever you're talking to in the company, say we need that more.
Okay, I will do that.
That little interaction stuff's fun, man.
Yeah. So here we go.
That's an Anthony's birthday.
Oh, you know what? I'm going to do this with a mouse and with a pen. Okay. So first, I'm going to do the red line. It's going to be really fun doing it from this direction. Okay. I may not be able to do this. All right, let me do it. Let me do it without that. This is what you're talking about, right? You have a second set of batteries. Okay. So effectively, we have our battery 1 negative, right? Battery 1 positive, battery 2 positive, battery 3 positive. That's the first one. 4 connections makes sense. We go to the second set. All we need is a battery 1 positive, battery 2 positive, because the battery 3 positive is actually measured at the same voltage as this one. So we assume that you've got a good connection here, okay? We sometimes are wrong, but overall we assume there's a connection here. That's why you don't need the third one.
So what happens if that bottom one just takes a dupe?
If this one takes a dupe, it can't because it's physically connected to this one.
Oh, okay.
So what would happen is the balancer, right? the balancer actually is going to balance this one to this one, and this one to this one, this one to this one, right? So it's all balancing. It's also going to balance this one to this one. It's going to balance this one to this one, this one to this one, and then this one to all of them. So it balances. It works just fine, no issues. Make sense?
It makes total sense.
Yeah. It's that's a great question. Thank you.
It was never explained like that. Sorry.
Yeah. Well, that's what I'm here to do. What other questions do you guys have?
Is it on the status line? Leads?
Yeah, that's the
Status monitoring leads,
big
same
yellow
thing.
green ones.
I haven't wired up with that.
You will be. It's all good.
If I'd have thought about it, I tried to bring mine, but I lost my status because of COVID. I haven't been flying around enough. So I can't put a 70-pound power supply in my bag and bring it up here.
Well, they won't let you take that on a plane?
No, if I pay them an extra $100, they won't.
Yeah. Airlines.
Other than the SFP slot, what's any other differences between the 3 and 3.1?
Wow, there's a ton. It is a more soft power supply. So if I brought up the web page from an XM 3.1 and showed you the amount of components that we can now interact with, so we now, like, how many guys have been talked or have talked about an XM 3.0, XM3 capacitor problem? Nobody? Okay. So the caps sometimes will go bad. The XM 3.1 actually will look at the cap and give you an estimation of how big the cap is. So that's plus the apps board used to be a separate module behind the front panel on the XM3. It's now built into the modem. This modem has 8 gigs of RAM in it. So that gives you an idea how powerful it is. I mean, it's effectively a computer. It has 2 cores. An XM3 modem is a DOCSIS 3 modem. An XM 3.1 is a 3.1 modem that is a gateway. So this has an e-router, it has firewalling, everything else built into it. So again, we figured that based on small cells and stuff, and I have another presentation I can show you that, this unit can work with a small cell. You can plug it right into the SMP port. We have a PoE converter or a 120 converter that works with it. We can drop a small cell right here. That e-router actually helps the small cell work better. So it's a good couple of questions. It's fanless, again, so no fan to go bad, like the XM2s used to have. And the Faro is improved. It has a better Faro. We went from, remember R mode? Now we have like 3 forms of R mode. We have fine and other regulation. You can get to all of this through the web page. So that's one of the things. I have a little router over there. The number one thing, your number one friend for field diagnosis is your router, or 100-foot Ethernet cable, whichever you want to use. Because it's a whole lot better today to be working on a power supply, 5 minutes up, plug in, close the door, go down to my truck, work on the power supply.
How are you doing that?
Where's
Where's this router that we can get?
So we used to sell it actually at kit. I'll show it to you. It's a little battery operated router.
So you can actually just plug it into the Ethernet jack and run all your diagnostics from your laptop?
Yep.
No freaking way.
Yeah. So. Sure, I'm not connected or anything. So there it is.
That's it?
That's it.
And I don't think they have it on a web warehouse.
Maybe not. Yeah. But this is a little AP router.
Yeah, I need to take a picture of this thing.
It's a TP link here. There's the stuff.
Yeah.
But so, and what I do, I don't know if you noticed, there's a little antenna sticking out of my PC. That's a second wireless card. So here's the reason: either use the Ethernet or use the wireless, because your IT department normally will not have a problem with you connecting that way. The one advantage you have in the wireless versus this. With this, I'm going to have to set my computer to 192.168.100.maybe 10. Your IT department may not allow you to change or hard code your IP address. With this, the IP address is on the other side. So all you do is attach to the Wi-Fi and log in. It gives you the address in the right range. So it's just kind of a nice thing.
Yeah, we can change the IP address, we just have to
So-
request access to it.
Is that same thing as if I click in the IP address and the actual power supply, it brings up to all the information? Is that the same thing?
Not exactly. So there is a standard host within the transponder.
Okay.
If it doesn't connect to a DOCSIS network, it'll bring up its own internal network, and that's the 192.168.100, and it'll be .1. That's the gateway in a we'll call it Class C a /24 255.255.255.0. But when you get a cable with a config file in it, they can overwrite that. So it can effectively be told, no, you're now on the Comcast network and you're getting a 24.10.6 or whatever address. If that happens, if you can't get connectivity to it, unplug the RF cable, pop the inverter, it'll reset it. So on fire up, it always comes up with its own until it's told to get the other address. So do everything you need to do, and the last thing you do is hook up the RF cable. While it's coming up, check your RF levels and everything, and eventually it'll go off because it'll now be a Comcast network with firewalling, or they can turn off the web page. So Comcast has complete control over that. This is one other thing. You asked a couple of other, what the differences are. So we're now doing RDKB. Are you familiar with that term? Yeah. So the Comcast standard, this is just like a Comcast modem now. So password of the day, automatically programmed, everything's ready to go. All of the advanced features, TR69, all those type of features running in here. So that's, like I said, that's about it for me. I think I'm at so thank you, everyone. Yeah. And I guess we just need to cut off the live feed.
Let it run.
Well, I was told to be done at 11, so I think so we can get you guys some lunch. Oh, we should say yes.
A couple guys are coming. Well,
We could just
I
click
think
stop
maybe
streaming.
I wonder when they start making it lighter.
Maybe you already clicked it.
Accent 300.
he's not coming at
Which
all.
ones are there?
They're the ones replacing the
He's
main
getting-
group.
No, I haven't seen. Oh, you know what
Yeah,
I've seen?
sorry about showing up late. I didn't.
Good afternoon, everybody. My name is Ben Strunk. I'm the Critical Infrastructure Director for Comcast Cable. We're here today at the Eastern PA chapter of SCT to go through critical infrastructure and how it is supporting the broadband age. As we go through some of the documents and the materials today, we'll be showing you some history on the critical infrastructure facilities. We'll be showing you some of the advancements, some of the technology that we're doing to enhance the critical infrastructure side of the cable MSO network. We can also go through and actually explore what could be coming up in the future. So one of the best ways to talk about what's going to happen next is for us to look through at what happened in the past. So with that, we'll go ahead and begin. So what we wanted to talk through first was the cable TV network at its inception. At its inception, it operated around a 250 megahertz operating frequencies. And as you can see, the buildings at the time, the critical infrastructure at the time, was really based on that one single one-way directional flow of RF signals. As you can see, this is what it used to be like. You had a building that supplied RF into a trunk amplifier, and then to the power supplies, and then downstream. It was always a one-way directional flow. What's interesting is that when we think about where we were at the very beginning of a critical infrastructure stage and the processing and the distribution of the signal out to our customers, we would think that this was in the 70s. In all reality, this type of infrastructure is still used today. It's robust, it's there, but it is still an active infrastructure. As we do look at everything, you have a regular building, you've got a facility. At this time, all the critical infrastructure was maintained maybe by a backup generator. In the originations of the entire facilities that had to support the broadband side of the world, critical power wasn't necessarily available. UPSs weren't available. DC power plants were pretty much a feature only within the central office exchange systems from a copper tip and ring type provider. It really wasn't needed for the delivery of video signals across to the masses at the time. But then we move into the next round. So 330 megahertz two-way systems for content delivery. Again, we're looking at sheds. We're not looking at anything that's very robust or critical, as we'll say, or in conjunction with anything that's a modern effort. But as you can look at everything, it was sort of the next gen. What can we do next in the video platform to actually achieve some level of enhanced product? And we got into the controller age. This was a two-way type of RF system. When we were looking at this, we were looking at more of a hub design that was able to go back and forth within the networks. Critical infrastructure still was in its infancy. It was really based on air conditioning for just a small load, maybe a 3 kW load, maybe a 5 kW load. It really wasn't that robust. You still had generators. You might have had a UPS at the time just to handle some of the power blips. But it really wasn't anything massive or what you would see today from a data center architecture. But it worked. It was reliable, it was consistent, and it provided a product that the masses that were paying for it, the subscribers of the time that were paying for it, was okay with. They were good with seeing what they were seeing. But yeah, this was what had to get controlled. As we look at the next type of building, we moved into the 550 megahertz side of it. You have a more robust structure, you have a generator, more robust air conditioning, fencing, security. You are actually providing a much better resilient network. You could actually see that some of the architecture started to advance to DC power plants and battery backup systems. You were looking at powering up not just the RF and the video signals, you were more along the lines of backing up the entire network, a core network, a routing network, a transport network. You were actually doing things that was enabling the broadband side of the world at the time. But then you had a deeper concentration within data center activities, master head ends, hubs. All of those different buildings and all of those different facilities cohesively together was providing a critical infrastructure. Most of the times you would think that the critical infrastructure was mostly just at the facility level, but it's really the entire ecosystem of every building coming together to provide a reliable, always-on product. So you have the data center side of the world that was talking to the master head ends. You had the master head ends talking to the hubs talking to the outside plant nodes, the nodes talking or being powered up by the outside plant power supplies. All of this was really the originations of a infrastructure. The infrastructure enabled the network, the infrastructure enabled the content delivery, product enhancement, product improvements. But it all came down to that robustness of the actual facility layer. Then, if you really want to imagine it, now we're getting into a 4th generation cable technical facility, which is mostly large central office size locations. You can see that you're moving from wall pack air conditioner units to full data center crack units. You're looking at multiple rooms carrying different products, multiple building locations that are separated. You've got fiber ties, you've got a whole bunch of different infrastructure that is really enabling some of this stuff. You've got large industrial size switchgear. A lot of this industrial size switchgear is because the kW and the amperage that's needed to support this much infrastructure and broadband compute and processing really is the driver for a lot of this infrastructure. The amount of electrical distribution went from a small 200 amp single phase in the smallest of the buildings to a 1 megawatt distribution system. That 1 megawatt distribution system is really what's enabling the next gen routers, the CMTSs, CCAP boxes, linear video insertion into the broadband spectrum. A lot of this stuff was really driving to a more robust, always-on technology. Larger generators that are doubled up. They're in what's called an N+N relationship. So with a lot of this stuff, you can actually see that there's been a focused effort to make the ecosystem of the infrastructure as good as it can get to provide what the customers were looking at. So you can see from the smaller or least amount of time frame, or the oldest technology out there, it really came down to the core components of it. It came down to electrical utility service, conditioned power, air conditioning to cool space, backup power with a generator, and a solid, robust facility that's actually able to handle the loads that we're talking about handling. So what does all this look like in general? I've got a movie that hopefully it'll end up playing through here. Maybe. This is one thing I didn't check out. Oops. No, maybe this one's not. How isn't this one right? Sorry, everybody. Not sure why that's not gone into present mode, Mike. That's the slideshow. Could be. Let me see if we can just. Here, let me do this real quick. Sorry about this, everybody. Escape. got that tagline within at the end of it. So as you can see in the film, that's just one of the ways of constructing a broadband building that is enabling or housing the critical infrastructure for this next gen or the future broadband era that we're working in. So one of the next things I wanted to talk to you about was there's not one critical infrastructure solution for everything and any problem that we face. I'll just go back and try to manually keep this going. So there are residential neighborhoods that sometimes we have to work and build our critical infrastructure around. So as you can see, you can't probably tell where the critical infrastructure facility is in here unless you were really looking for it, and it's right here. Most of the times when you're talking through critical infrastructure engineering and architecture, we actually have to build some of our buildings to facade into the existing neighborhoods. As you can see in this image, we actually made the building look like a barn or look like a garage. It actually was trying to blend in with even fake windows to the site. You can tell with the electrical infrastructure coming in, we've got all the AC electrical infrastructure coming into the new building, and it really hides in plain sight, which is one key factor that we try to architect into our properties. Again, this is 150 kW service. We were actually able to make it look like the existing building without letting anybody really understand what's in there. Fake windows, false roof, secondary roof, which adds a layer of water and protection on the inside. But as you can see, as we go into the actual building, it looks like a modern broadband center. You've got suspended ladder racking, you've got fiber duct, you've got fiber entrances, FM200 system, alarm and annunciator panels. This is really what makes up the backbone of a critical infrastructure site. All of those things to enable what we need for a modern networked engagement building. Talking through some of the infrastructure that you're going to see typically in every site, you've got a DC power plant, you've got what's called a battery distribution circuit breaker bay, you've got an inverter system, you've got batteries behind it. Obviously, when you talk about infrastructure, infrastructure really can't do anything without some means of fiber connectivity. So as you are going through and architecting and understanding what your facilities need to be, you'll have to be cognizant of fiber entrances, OSEFs to splice in outside plant fiber into patch panels and into preterms and umbilicals. We also need to be cognizant of what's called a TVSS, transient voltage surge suppressor. So a lot of this stuff is really key to the work of a critical infrastructure space, and that is really what makes up a lot of the resiliency of it. But then you have a different way of constructing things. So in this application, we have a small original modular critical infrastructure structure that outgrew its usefulness. We needed to modernize, we needed to double the size. Even though we're in a network space right now with remote PHY and with full duplex and with everything that the technology advancements of the MSOs are going through, we still have times in which the buildings we have are still too small even though we're miniaturizing the network. So as you do get into a building expansion, what we decided to do in this location was we decided to build a brand new building around the original building. By doing this, we were able to keep all the core network elements within one spot, the same spot that they were in today. And that was actually a cost-benefit analysis. Whenever you are architecting some of your critical infrastructure, you need to be cognizant of, is it cheaper to move a building? As you can see here, we literally moved the building, or is it easier to move the network into a new structure? In this application, it was easier to relocate the walls, the roof, and leave the floor of this existing structure and crane it out of the way. And that way we didn't have to relocate fiber, we didn't have to relocate nodes, we didn't have to relocate the power system and certain electricals. It really is a unique way to look at any critical infrastructure solution. As you can see right here, this is us putting the concrete deck planking back onto the new roofing structure for the location. And at the end of the day, you have what we would call a resilient hardened structure. You have a full CMU, a full CMU back building. You still have a new generator. The roof is watertight. It uses what's called pre-tensioned steel decking and planking. This actually creates a very good, robust roofing system. So that's just a second way that we deal with critical infrastructures and how we need to transition them during this broadband era. So we can look at another modular building technique. With a lot of these modular building techniques, you do get an inherent portability within your critical infrastructure. You can buy a building now with your air conditioners attached to it. You can buy a building now with your DC power plant, your UPSs, your inverters. Everything can come pre-ready and pre-factory built. It's almost like one of your modular homes. It comes with the carpet already installed. It comes with the fireplace potentially already installed. But with this one in particular, as we click back through it, it comes in a section, which is very important because you need to be able to integrate all of your AC electrical between the multiple sides of the building. And then as you set everything together, you have a pre-engineered slab and foundation, pre-engineered fiber entrances, and it really comes back down to a development technique. Whenever you can't just ad hoc a critical infrastructure building time and time and time again like a Medusa box. You really have to engineer to a solid site plan. You have to engineer, excuse me, you have to engineer to a solid design criteria and solid standards. But then you get a finished product. The finished product is what's interesting because your time of delivery is very low. Your time of assembly is again very low. And you can put whatever you want into it from your design standard. In this building in particular, we added a solar system to this property to make it more energy resilient. We were able to make it with the solar panels an OPEX savings by not spending as much of on electricity. And it also helps get the buildings to a more carbon neutral structure. So you can't put solar on every building. We all have talked through that. The questions that come up to me a lot of times is, why can't we do solar everywhere? It's still not practical. You can take a chunk out of it every time you have an opportunity. You can put stuff in for today that you might not be able to see a real payback until tomorrow. There are some more techniques that we utilize. This is called a tilt-up concrete wall construction. Instead of actually being able to cart in a whole building or cart in and do CMU masonry, what we were able to do is pre-engineer concrete panels that get welded together. And by doing this, you're actually able to lower your construction costs. You don't need a crane, you don't need heavy architecture, you don't need heavy materials, you don't need a pumping truck, you don't even need a lot of CMU. But what you did need is just be able to lift up some concrete pieces, and before you know it, you've got a solid structure with a solid roof that you can bolt onto an existing cable building or an MSO critical infrastructure space. Again, this comes down to pure planning and a cost benefit as you're trying to figure out your structure and the purpose of what the expansion is going to do for you. This next technique is an interesting technique that I've had a lot of success with. This one is called an insulated concrete form wall. This allows you to actually construct an entire building around an existing building and actually be able to do it in man-sized Lego blocks. So as you can see in the image here, you're building the actual structural wall out of pre-insulated concrete foam, which allows a concrete interior to be placed inside of the foam as you erect the building on top of the existing building. Less intrusive, it's a lot easier to get up and down, and it's a lightweight product. The product is very, well, it's styrofoam. It's by default light. But what it enables you to do is you can actually manipulate the building size and the wall sizes based on the structure that you're trying to overbuild, which that was a key to this design parameter for this location. And as you can see it, we were able to put in all of the DC critical infrastructure that's needed for the space. The air conditioning is able to be right placed. And before you know it, this is what the structure looks like. It really is a modernization effort from an old building that cannot meet the requirements of the broadband age. And you're actually able to repurpose everything again without moving the network. You don't have to move your core routing or your nodes or anything from that perspective. And then we actually have to look at what fits. Sometimes you'll get into into a location where it's an old legacy cabinet. It's the true optical OTNs for everybody that has lived and breathed the cable side of the business. In these applications, you'll find out that it's actually better to collapse them and eliminate the entire property than try to expand it. When you think about it, there's some very finite decision metrics that you can use. Is it expandable? Is it a lease? Is it an easement? Is it a robust location? Is there high traffic? And in most of these locations, it really wasn't scalable. You couldn't do modern products. You couldn't expand and offer the next gen product line that you might want to have because these cabinets were not able to be supportive of it. So you just eliminate it. You effectively just move the network traffic to another critical infrastructure facility, and you're able to make the best of the product that we've got to sell. So now we'll go and talk through some of the stuff that is really the engineering nuts and bolts of the program. So we had what we called at one point the capacity balance beam. What it is there's a beam. Let's just take it quite simply. So you have a beam here, and you've got to measure growth. Growth at the critical infrastructure facility could mean you need batteries, you need a generator, you need additional air conditioning, you need additional space. The modern critical infrastructure engineer should be able to evaluate all four of those items in order to make up the best decision. Coupled with growth, you have to choose or identify what your available headroom is. The available headroom that you've got is going to determine your level of investment. And as everybody is cognizant of cost per watt, cost per delivered bit or byte, cost per anything, you have to really understand what you've got as available headroom versus what you have for growth. Now when you take a look at this, now you've got a fulcrum effect. The fulcrum effect is really your capital. How much do you have to spend? Because when you look at it, you can spend a lot of capital to increase your available headroom because you've got a massive amount of growth coming in. One of the other ways you can do it is you can focus your capital on your growth, not on your available headroom. So what that means is you have to determine when you're really evaluating your critical infrastructure needs, do you want to spend a lot of capital to support your growth or a lot of capital to increase your headroom? Because when you look at the balance beam, you have to find that middle point. The balance of capital is going to be important. And then finally, you also have to look at the other things that you can bolt onto this capacity balance beam. Removals. If you can tie removals causing a drain on your critical infrastructure against your growth, you can actually balance out more of your capital. You also got to layer in your opportunities for efficiency. Efficiency improvements are really going to bear zero cost fruit to your available headroom. The more you can make efficient, the less money you have, the more you can actually do with your available space. And when you take a look at all of that, that's sort of where you get your balance. You're trying to create this balance of, do you spend money or do you conserve space? And I think that there's a fine line that you can do both. Making your sites more efficient drives down an OpEx. You have to spend less capital. You really have to be a steward when you talk through your critical infrastructure investments. So what that balance beam does as we're talking through the critical infrastructure spaces is you really have to come up with your decision tree. Now your decision trees are really based on what you can do and how you have to level set your mind. So level of site inefficiency. it really is important to know where you can actually make your efficiencies improved and where you need to. Age of equipment. As you're talking through on that balance beam, you're talking through growth and offsetting the capital investment. One of the decision points to keep in mind is the age of your equipment. If you have old, non-robust equipment, it might be wise to replace it and spend your capital. No matter what you do with efficiency to make space for today, you might not be able to save the capital for tomorrow. Airflow improvements. We didn't really talk yet on airflow for air conditioning as a matter or driver of critical infrastructure, but airflow improvements really lend to this circle of decision that we're trying to walk ourselves towards. Capacity reclamation. Capacity reclamation ties hand in hand with level of site efficiency, age of equipment, and airflow improvement. But the real thing with capacity reclamation is you're actually able to do more with what you have than you used to. Because what's going to happen is you're going to walk yourself to this right decision, which is right here. And that right decision is going to really determine your investment size. If you can think through and get 4 improvements for every $1 spent, you've made the right decision. And when you're talking about critical infrastructure where your air conditioning can cost anywhere from $5,000 all the way up to $460,000, you really need to make sure that that decision of today is really going to pay an IRR back to you for the 20-year life expectancy of that air conditioner, or for that generator, or for that DC plant, or the amount of batteries you have. So even though we're talking about airflow, capacity reclamation, age of equipment, and level of site inefficiency, it really ties to all layers of your critical infrastructure ecosystem. Your building, your generator, everything that goes in to provide that one piece of bit and byte traffic to go out to the customers. So how do I even go through some of the decision trees? So I was recently asked to speak at a different SCT event where we're talking through what kind of air conditioning should we use at a lot of our sites. And I really had to challenge myself and try to figure out how many different solutions are there. So I really had to put them down. There's passive, evaporative, temporary, in-rack, permanent, dumped, chilled, directed, liquid, velocity, ambient, phase change material, flooded, compressive, ducted. Every one of those air conditioning solutions are really driving what your decision can be. Because just like what we talked through on the structural side of the critical infrastructure building, not every decision for air conditioning is correct too. You can't use one decision to solve for 1,600, 2,000, 4,000 problems. It's just not practical at this day and age where our buildings were not built originally the same way. So these are our different options when we talk through cooling the critical infrastructure space. So as we see some of the infrastructure for cooling today, it sounds a little bit weird, but these 2 window units cooling this building, granted this building is a legacy building that's only got a one-way system on it, that was probably the right financial decision for that building at that time. It was cheap, it was simple, it was reliable. The technology and the hardware within that critical infrastructure facility was not really needing a conditioned space. It was just needing a cool space. So when you take a look at the needs of the equipment, and I'll give a shout out to some good friends of mine at the Downingtown Lab in Downingtown. They're evaluating the thermal dynamics of equipment. They're evaluating, can this equipment survive a building that operates at 80 degrees, 90 degrees, 95 degrees? And it really struck me as we look at our own outside plant nodes and our own outside plant power supplies. They're using ambient cooling technology today. So if that's the solution for their critical infrastructure space, what can we do in the buildings to provide the same level of resiliency and utilizing the cheapest form of cooling possible? I'll go off on a side tangent because I think it's value for everybody to understand what's on your surroundings. If you haven't really searched it out lately, When you're driving around a town like Washington, D.C., Houston, Baltimore, Pittsburgh, Pennsylvania, if you really look close, and this is one of those things that once you see it, you're not going to be able to unsee it. Look at the telephone poles. Look at the street lights. And you'll start to see little boxes that are popping up all over, and there will be like tubes on top of it. What that is that's called a 5G pole cell. As the wireless carriers were prepping for a 5G rollout for all of the infrastructure to enable the cellular network of the new era and the bits and the bytes, it's interesting because they decided to build everything to be on an ambient cooling platform. They don't have active fan systems. They don't have, compressive cooling at all these small cells or pole cells that they plop all along the cities, all along these little towers. And it's really interesting how they were solving an OpEx problem and a resiliency problem with a product solution that enabled it to work within an ambient temperature zone. So, not to pull you back into it, but yeah, when you're driving around, take a look and you'll start to see some of those things, and now you'll not be able to unsee them when you do. So the next type of building and the next type of cooling from a critical infrastructure cooling technique was the tried and true. The one thing that we've got 100,000 of out there in the communication world are these wall pack units. It's a self-contained air conditioner with a compressive, evaporative section down here, airflow coil systems, you've got a controller system, and you've got a filtration system. But these type of wall pack units, they were mass-produced. They are mass-produced. They're utilized not only in critical infrastructure telecom buildings, they're used in temporary churches, they're used in temporary schools, meeting houses. You can actually cool your own shed with one if you wish to. But as we in the communication industry have been talking about cooling for a small structure, that was the best way to do it. It was using effectively the terminology that I've used and I've seen in the past was, you're cooling the refrigerator. You're not making the best investment, you're not making the worst investment, you're cooling the space in the best means possible for what you have in the building. It works, it's reliable, it makes the equipment operate at a good temperature, but it is very non-tactical. And that's sort of the thing and the theme of walking through a lot of these different critical infrastructure cooling techniques. The next is what I was calling or would call a hybrid system. The hybrid system itself takes care of a multitude of different cooling opportunities based on the buildings that we've got. You have a normal wall pack system that is a highly dense 10-ton system in an N+N relationship. And then you've got a package system which is based on a RTU technology, rooftop unit technology, where it has everything self-contained in a packaged or a skid type architecture. As your mechanical engineers or your critical infrastructure engineers are solutioning for the best solution for the building that they've got, this is a good solution. You have air coming in through these curbs are going in through the ductwork is making its way into the building, a return is coming out through the building to get back into the mechanical cycle. You have an N+1 or N+2 capacity on your air conditioning. A lot of this stuff is tried and true and is a hybrid solution. It works. You're getting the best of both worlds. You're getting spot cooling here where there is a defined load, and you've got flexible ducted cooling here that can go through a balancing effort each year as you need to or as you add additional load. As you can see on the inside, now you've got a few different flavors. You have a ducted system through these crack units. They're going on what's called an upflow system. The upflow system allows fans to push air up the ductwork, over through your infrastructure, through your building, and then be placed in a cold aisle environment through the ductwork that is able to shoot down in front of it. This is a good technique. It's a ducted technique. People have used ducted techniques for hundreds of years. You have a ducted technique in your own house. I don't know anybody that really uses a flooded system in your own house because it's just not efficient. But what this does do is it starts to layer in a level of complexity. Whenever you add a new piece of load, or as a critical infrastructure engineer, you approve a new piece of load, you have to understand that there's a correlating BTU value, British thermal unit, that is really going to drive additional airflow and an additional tonnage calculation. So we being critical infrastructure professionals, you need to be able to analyze what your ductwork is capable of providing, what the equipment consumption is, and what the new equipment consumption is, and that you can accurately and availably provide cooling to your space in a resilient, resound manner. So that's another means of cooling systems. Now you have the onslaught, and I'll call it the onslaught, of what's called tactical cooling. Tactical cooling is, I've heard some of my peers call it supplemental cooling. What it is it's cooling that's allowing a defined set of air to solve a defined equipment problem. So in some of these applications, like the one here on the right, this is a in-rack air conditioner. Literally, some of the manufacturers have found a way in which a good solution, we've all walked into it. In the wintertime, you're walking into your favorite restaurant or you're walking into a new building. You'll feel a curtain of cold air or hot air come down over you as you open up the door. Effectively, this is the same thing. You are generating a curtain of cold air that's allowing cold air to float directly in front of your specialized piece of network equipment, and it's able to provide that instantaneous 75, 70 degree cool air directly into the inlet of that unit. The reason for some of this tactical, I'll preface that, this on the right-hand side is also a tactical cooling system where you're using pumped refrigerant inside of the rear of a cabinet, or the front of the cabinet, depending on the manufacturer. And what you're enabling there is you're able to capture all the heat before it comes into the room and it becomes a flooded environment. The key with both of these is, as you're evaluating your capital balance beam, you're actually able to determine there's no need to really throw out your existing critical infrastructure cooling space because you can't solve for this one problem. Supplement it. Go after a tactical solution that allows this critical infrastructure piece of equipment or this critical infrastructure piece of equipment to solve the direct need of your new internal customer product that's going into your critical space. So a lot of this is really defining, you can either go inefficient and large, or you can get really tactical and small. And it really is based on what you need to solve for within your ecosystem of your critical infrastructure facility. This is one of my favorite ones too, temporary cooling. Again, I'll go off on a tangent in a side story. LEED certified buildings. LEED certified buildings have a set criteria for how much energy you consume versus how much energy you use to operate the building. Movie studios in California, it's a great example of it. Movie studios in California were trying to figure out some way to become LEED certified. So what they decided was, hey, you know what? I might not be operating 24/7. Why do I need air conditioning 24/7 in these studios? And some of their architects started going through the LEED certification process and going through all the paperwork and the charts and the diagrams and the tables and all of the product that you need to do to become LEED certified. What they figured out was, you know what, you're right. If a studio soundstage is only being operated 3 days during the week, why can't you just bring in temporary air conditioning? Why can't you just bring in temporary lighting? It doesn't become part of the entire building, and when you're done with it, you turn it off and you take it away. You take it to a different studio, you take it to a different warehouse, you take it to a different location. It really was an interesting mindset that why have an always-on cooling system when you don't need it? So you got this temporary stuff. Now granted, temporary stuff we would think is more of a disaster recovery, or the main system failed, or something just isn't working right, but I'll tell you, it's actually quite elegant as a solution because we're in this technology bubble in the technical facility space. When we're seeing new equipment come in, we have a finite amount of capital to control and cool it. But we know that something else is coming out. It's the business intelligence of how do I handle this bubble growth of critical infrastructure? Well, utilize temporary cooling. It is really a good way to deal with it. It's a temporary solution to overlap this bubble, and then you can just take it away and use it at the next site. Very rare, well, I won't say very rarely, but hopefully in a technology refresh world, you'll be going site by site by site by site by site. When you're going site by site by site, you're enabling the opportunity to use the same temporary solution, hopefully in a multitude of sites, lowering your total cost, lowering your transition time frame, and enabling your existing infrastructure to keep being utilized to its fullest. So don't be afraid of temporary solutions for a permanent solution. It just doesn't work today, but it'll work when you're done with your bubble transition of energy. And then we've seen this picture before. I put this here in jest, but this is ambient cooling. We're not really taking advantage as much as we can for ambient cooling. Again, I'll talk through the work at the P&E lab in Downingtown. They're great at trying to figure out the correct temperature that equipment should be operating at. We as critical infrastructure engineers and operators need to understand that if the equipment can operate at a higher temperature, let's utilize free cooling a little bit more. Free cooling doesn't need to happen when you're just suddenly below 55 degrees or 45 degrees. Free cooling can happen when you're at 60 degrees, 65 degrees maybe. It all depends on the equipment, and it all depends on how you're architecting your solution. Don't be afraid of it. It's something that's going to save you money in the end. So the reason why I'm talking through all this is we're talking cooling in the critical infrastructure space to get down to what is the simplest means to protect our broadband customers, to protect our buildings from a resiliency and reliability phase. And it took me back to my history in operating ships. Way back in the day. We're talking back in the day of the Titanic. We're talking back in the day of Liberty ships and Victory ships and things like that. Seafaring engineers actually realized that they could cool their entire power plant just by the movement of a ship through water. So when you think about the most simplistic way to operate a steam system, a condensing system, an air conditioning system, a vacuum system, water purification system, if you can actually just harvest the speed of water that comes from an inlet scoop to the outlet scoop and utilize that speed of water that's always at a 55 degree temperature or less, 30 degree, 40 degree, now you've actually been able to save a lot of fuel. You've been able to actually save a lot of your embedded kWh. And that, I think, is one of the biggest keys as we try to solve as an industry our cooling scenarios and our cooling problems. How can you use velocity and free fluid flow to solve your air conditioning problems? I think that there are ways and means. There are companies out there that have utilized a Venturi effect. There's pumped refrigerant. There is a multitude of other things on the tactical and sledgehammer scale that we can actually use to lower our operating cooling costs. So simple is usually best, and I think people from 100 years ago figured that out. I think that it is good to know that as you migrate to maybe a simpler solution, it does become more reliable. And I think that's a benefit that we need to explore. So it's passive, it's unlimited, tons of cooling capacity, and it's simple. If you want to take something away from this conversations we're having on critical infrastructure, keep those four things in mind. If it's simple, it has tons of capacity, it's almost unlimited, and it's passive. That is a guiding principle for your engineering solutions, and your engineering designs are really going to pay you back on your OpEx side of it and on your preventive maintenance side of it. So I'm going to just click through this just so that you guys can see how we've developed or figured out where things should be. And we were talking through this with some of my peers regarding just a simple box to evaluate your cooling opportunities between complex, simple, energy, and redundancy. And you can see as we're talking through all these different things, they all have a different primary objective and secondary objective. If you want to save energy, which we all want to do, look to and explore your opportunities for passive or ambient cooling. It's going to save you the most energy. If you want to look at complex, because that's the environment that you're working in, then you're probably going to look at a dumped, a liquid, a ducted, a flooded, or a permanent solution for air conditioning. If you want redundancy at our data centers and at some of our larger critical infrastructure facilities, you want to look what would be called in-rack or compressive or chill water or directed. That's probably some of the best ways of redundancy cooling opportunity. And then you've got simple. Simple is temporary. Those sliding coolers, just to cool what you need to for a month, a week, a day, whatever it might be. Velocity. Velocity cooling is one of the things that we really haven't addressed too well from a critical infrastructure perspective. Velocity cooling is effectively, you're just using the volume of air in a quick manner to eliminate the heat. It's effectively what a heat sink does. Or our outside plant power supplies are using a level of velocity, it's just the wind blowing across them. And then PCM. PCM is a phase change material. The best way to describe a phase change material in the critical infrastructure space is, I'll give you a real world example. I'm going to go out and I am going to have a picnic and I have bottles of water and I put blue ice into a cooler. Blue ice that you freeze in your own home is phase change material. As we grow with technology, we can actually cool buildings with this blue ice sitting there by a fan cooling our network. It's very elegant, it's very simple. So don't be, when you are doing your entire review of stuff, keep all that stuff in mind. Now, it does get you to an energy savings. Digital is better than analog, as we all know, and it saves you energy. Energy saves you money. So that is how we would formulate looking at cooling in the critical infrastructure space. Talking through it a little bit more, and we'll just flash forward through this. You've got room, which is your least efficient structure of cooling. Row, which is better. Rack is good. Component level is most efficient and effective. This is a thermal image of one of our core routers. It's really interesting when you take a look at things in a thermal state. This is the heat that's coming off of this chassis. As we're talking through the efficiency side of our capacity balance beam, you can actually see where this unit is not very thermally good. It's actually putting off probably half as much load and heat as it is in processing. And that's something we got to really be cognizant of. And as critical infrastructure engineers, we should be empowered enough to challenge some of our embedded thoughts and our embedded push downs, we'll say, of hardware. We can build a house for anybody's hardware. We can operate anybody's hardware within our house. But sometimes when you look at something like this, we should challenge it and say, what is the best way to cool it? What is the best way to operate it? And how do we build an ecosystem for that box within our facilities? Now, there is some good things that we do, and there's some not good things. But we also need to talk through some of the risks and the hazards in the critical infrastructure space. So we operate batteries. Batteries are a necessary means to operate a resilient network. It stores our energy for when our first layer of energy is not available, when our utility grid isn't available. So what will happen is that you do get some critical failures of batteries. And in this case, you can actually see where the battery actually melted its way through and actually burned its way onto the battery stand. This was not a good day for this battery vendor or this battery manufacturer because what that did make us do was, that was a result, that's how bad the battery melted its way through And this is what we actually did to try to figure out what happened to the battery. So we actually had to break the battery. We had to cut it apart. We had to do some sort of forensics to try to figure out what happened. And as you can see, where this melted out at the base of the battery where it made contact with metal, it actually generated a solid short. And that solid short, luckily it didn't take down the DC power plant, but it did cause a whole bunch of smoke and a lot of bad stuff to come in. But this was the internal damage of the battery as it started to liquefy and melt off its own electrolyte within the plate and the frames. It really wasn't a great thing to deal with, but from a learning experience, I think a lot of my engineers at the time and a lot of the manufacturers were able to get some good intel out of this and how to make batteries better. And I think that was a bonus or something good from this. So battery went into a critical short due to an acid leak, and that's what we figured out was the root cause of this. Now, one of the other things that we need to be cognizant of from a critical infrastructure operator perspective is what is the macro environment that we operate our buildings in? And one of the biggest things that we had to deal with from a macro environment, and I'll just take this from something we talked through, was the regrettable campfire out in California. So the Camp Fire is one of the largest fires that I believe happened in 2019. It destroyed the entire city of Paradise. Totally ravaged it, burned it to the ground. It was horrible and regrettably a loss of lives out in that campfire. But from our potential, what did it really cause? It caused a regulation change. It caused an operability change. It really caused potentially the bankruptcy of PG&E because of the potential lawsuits. It really tied into the power company failed to maintain a utility grid and transmission lines. As we talk through our critical facilities and we talk through our resiliency and our reliability, we first have to start at something we can't control. We can't control the utility power that comes to the building. Because we can't control the utility power at the building, we have to solve for their failure. It sort of stinks, doesn't it? Why can't we just always depend on this power being on 100% of the time? Because we spend a lot of money caring for that 96 minutes every year that a critical facility might be on generator because of a loss of a power outage. But you're going to see more of this. You're going to see more of forest fires probably degrading our reliability on a utility grid structure. So what's being done from it? There's been a push to do what's called microgrids. Microgrids are a way for a single building or a campus of buildings to successfully operate without a utility source for a long period of time. A microgrid is really taking advantage of any means of energy input and any means to utilize the energy while you're isolated and islanded from the utility structure. So we do see some microgrids going in even in our own areas. Being in eastern PA, in Elizabethtown, PA, it's one of the largest microgrids that have been around for a while. It's at the retirement village at the Masonic Homes out there in Elizabethtown. It's very interesting how they developed their microgrid. They developed their microgrid based on having access to natural gas on their own property. So what they did was they drilled down, they had their own natural gas, they have a tie-in pipe from the natural gas systems, but they're generating and operating their own microturbines. Those microturbines are actually providing a 12,000 volt utility grid that they own for the entire Masonic Home campus. That's a microgrid, and they've been using it for 15 years. They've also been tying in solar power and other uniqueness to their microgrid. The Philadelphia Navy Yard, that's on a microgrid system now as well. They can isolate themselves away from the power company and autonomously operate. Andover, Mass, Sterling, Mass, Penn State University. You can see San Diego G&E, ComEd, utility grid, microgrids. Even the power companies are understanding that they can't even rely on their own resiliency to keep their own power distribution and utility up and going. So this is stuff that we need to understand from a critical infrastructure perspective. How can we become more resilient and solve the problem from the power company's failures? It's an interesting problem that we need to all evaluate. But we need tools to evaluate it from. And what tools can we build? We're in this awesome compute age where we can actually build what's called digital twins. We've seen digital twins at the SCTE Expo show in Philadelphia this year. There were companies that were able to build digital twins of facilities, of buildings, of cell towers. This is a digital twin of an operating, not power plant, but a digital twin of an actual processing plant. So what the operators are able to do is they can tweak automation, they can tweak reaction times, pneumatics, they can tweak flow rates, thermodynamic loads. You're able to do all this virtually without actually impacting your processing. And by being able to check it first here and run simulation, you're actually able to make one tweak over here. Why is that important for the MSO community? We don't want to dabble in our stuff. We want to be hands-off. The common phrase I hear all the time is you don't have outages if you don't touch the equipment. There's some level of truth to that. It really does make it sound good that if I wanted to improve my airflow, if I wanted to see what happens to my buildings operating at 80 degrees instead of 65 degrees, a digital twin does enable that sort of view for you to reflect and isolate and learn upon. But then we got to also figure out what's coming next. So there's new technologies that are coming out that we're going to be exposed to, but we're going to be exposed to them in piece parts. You've got some companies that are very robust and going after lithium-ion batteries. They're pressing the battery button. And we are going to get something. We're going to get something like this eventually at our critical infrastructure space where we're not going to run generators, we're going to run battery backup units. We started to coin the term energy storage systems instead of calling them fuel tanks. Because as we do think of the entire ecosystem of our critical infrastructure, energy storage is going to be a better way to stipulate or state how we're receiving our energy. We are going to get to a point where it's going to be battery instead of petrochemical. We're going to have access to different types of photoelectrics. There's a company that presented out to SCTE in 2015 where they were actually able to harness super concentrated light and create just like a photovoltaic solar cell, 1,000 watts of energy within the size of a light bulb source. That's massive. When we think about what our broadband facilities might be like from an architecture period 5 years from today, you might be looking at a building that only needs 20,000 watts worth of energy. So think about the opportunities when you can actually power your entire building by 20 light bulbs, not 20 solar panels. And that's where we become very innovative, and that's where we need to be able to be accepting of innovation and enable this next round of critical infrastructure to come in. Phase change material, this is going to be big too, because then you can actually have thermal storage of energy, thermal storage of cooling, not just thermal or energy storage of electricity. If you can harness thermal cooling with energy storage, now you've got a building that can actually operate without petrochemicals, which is what we eventually should strive to do. And then you've got, buildings and edge compute locations that are going to be broadband centers hiding in plain sight. And that, again, is another thing that's going to benefit the customer base, but the critical infrastructure engineer of the future and the critical infrastructure is going to have to be able to work within a structure like this. A head end in the middle of a downtown park. You could find, a head end or a building or a broadband building, sitting in anywhere really. The furthest optical distance from the existing head end or hub, and then you can extend it and actually put it where people want it, not necessarily where we can have it. Because you're not going to have a broadband facility sitting there with a generator in the middle of the park. Everybody's going to say, no way, don't want it. I can't sit my dog here and I don't want to listen to a generator. So there are new technologies that's going to be coming out. So how do we gauge the efficiencies that we're going to get from that new technology? How are you going to gauge a lot of this stuff? What you're going to find is that you are going to see this inflection between energy and consumption, or efficiency and consumption, and you're going to find this inflection point. We're probably, because I know I built this slide about, well, in 2017. So 5 years afterwards, I can adamantly say that we've had some buildings meet this inflection point, and because of that, we're actually on the good side of the curve at this point. Where does all the power go? This is one of those things where you've got DC power, HVAC needs, consumed energy. The bad part about looking at a chart like this from all of our power and all of the energy we're providing from a critical infrastructure space, this is our opportunity of saving OpEx, saving critical infrastructure capacity. It's really something that as engineers we should be focusing on. And I know I jumped through a lot. I know I jumped through a tremendous amount of information. We've talked through broadband structures. We've talked through energy. We've talked through new technology. We've talked through the opportunities to really reinvent what we do from a critical infrastructure perspective. And I really hope that one of the best things that you guys were able to glean from this is not that I jump around and talk about 19 different things incoherently, but it's because every one little thing that you can do make the entire ecosystem better. And because it makes it all better, we're able to actually enjoy the fruits of our labor and actually create a product that our internal customers can utilize to actually make our customer experience better. So with that, I don't know if there are any questions from the field, Mike, or anybody, but I'm happy to take them.
So I have a question. First off, fantastic presentation. Earlier, in the beginning portion of the presentation, you pointed out that some of your sites use solar panels.
Yeah.
Has there been some kind of testing for like geothermal or wind turbines that you're aware of?
Yeah, so inside of SCT in what was called the Energy in Operation Sub-Working Group, every MSO that was part of SCT and the Energy 2020 initiatives highlighted or placed into a list all of the sites we used renewable energy, we'll call. I believe at the time there was at least, well, I'll speak to my side of it. In the Northeast Division of Comcast, or my prior side of it, in the Northeast Division of Comcast, they've installed over 2 megawatts of solar. It is powering up the network. It is powering up just like that building that we showed earlier. Geothermal was completed by Cox Communications about maybe 5 years ago. I know the engineers inside Comcast are looking at a geothermal solution to actually figure out the digital broadband buildings of tomorrow. Can you actually cool them 100% by geothermal? So on a wind turbine side of it, I know that there are evaluations going on. I don't know if they're to the point where we've got an operating system within any other MSO. I know Comcast does not have a wind turbine, but energy is energy. As we talk through the phrase that we used, energy storage, not necessarily fuel storage or diesel storage or whatever, energy storage from a wind turbine is absolutely plausible. We could do that tomorrow if we put a wind turbine up at some of our sites. What the hardship is on some of these technologies is, we'll take geothermal for example. In order for geothermal to work, you have to have you need to have a heat sink in the water environment to actually dissipate the BTUs that are consolidated into a fluid and then cooled by the surrounding geothermal substrate. You need acreage, I guess is the other way to put it. You don't need a lot of acreage, but you need to make sure that as you engineer your geothermal wells, you can't have overlapping heat sinks. So you need square area, you need footage. You can't just go deep, you have to be able to go wide. Solar is the same thing. You can put solar on the rooftop of every building, but it might only be like a 5% reward or a 10% reward. It really depends on the size of your building. On some of the buildings I showed, you could easily go 100% solar and power the entire building. Some other buildings, you can only do a 10 kW site, like what we've got in some of our sites, and that might only be 10% of the total consumption. It really depends on the site. And then again, as we're talking through wind turbines, there are high regulations as to how high you can go. And if you can't get up so high, you can't get enough velocity of the wind through a wind ROSA dial calculation to actually figure out if it's economical. So there are hurdles to doing a wind turbine. There are new technologies with helical as opposed to an axial that I think are promising. And there's no reason why you can't. It's really the impediment of the why don't you. So yes, you can do all of that. Yep. Any other questions from the group in the chat? Okay. Well, with that, I would like to thank everybody from Comcast Tech Ops for letting us broadcast to you guys from Downingtown, PA over this horrible weather. Hopefully this content kept you warm and happy. Would like to thank the SCT Central Eastern PA board for getting this training together. Feel free to contact me directly at Comcast if you have any questions or follow-ups, or if you just want to learn more about critical infrastructure. And with that, we'll say good day and see you at the next SCT training. Thank you. Does that work?